All right, I think we are ready to get started. Perfect. Thank you everyone for joining us today. We're really excited for this day of quantum. You're going to learn a lot about quantum, and then you're going to think of how to use quantum in our world, in our sector. So to kick us off with some welcome remarks, I have Cordell Schachter. Cordell, over to you to welcome us all in.
Thanks, Prachi. It's my pleasure to be here. Thanks, everybody from DOT and from outside DOT for attending. My remarks are going to be very brief. I'm under orders because we have such a packed agenda, and we want to make sure we leave time for all the things to come. I'm Cordell Schachter. I'm the Chief Information Officer of DOT. And we get involved in a lot of both existing and also emerging technologies because we want to be ready when they're ready to put them into place and to provide kind of a unified vision of governance and use across the department, and then to the various entities that we either regulate or the systems that we operate in national transportation. My responsibilities also include explaining complicated topics and technologies to our leaders, to our staff and stakeholders, kind of like Goldilocks choosing her porridge and her bed in the House of the Three Bears. Not too much explanation and not too little explanation, but just enough explanation so the new information and the new technologies can be understood and the information remembered and used by those communities going forward. Luckily, my time here today isn't to give you all quantum computing's Goldilocks explanation and use cases. That's for all of you to help develop and discuss during the day today, led by our distinguished speakers and facilitators. I believe quantum computing may be a more important topic for DOT than AI, which, in the last year or so has really grabbed everybody's attention. I think quantum computing may have real impacts in the transportation sectors sooner than AI or Gen AI. And because of that, I believe DOT needs to understand how quantum computing can improve safety in transportation, and DOT needs to be prepared to respond in kind when adversaries attempt to use quantum against us. Using quantum computing in the future may be the only way to successfully defend ourselves against malicious uses of it. So I'm very excited that this is kicking off, and it's going to be probably the first of many discussions here. And I wish you all a productive day. We're very glad you're here. It's now my pleasure to welcome Gretchen Campbell, the Director of the National Quantum Computing Office of the White House's Office of Science and Technology Policy.
Great. Thanks so much, Cordell. As Cordell said, my name is Gretchen Campbell, and I'm the Director of the National Quantum Coordination Office, as well as the Assistant Director for QIS at OSTP. So first, what is the OSTP? So the White House Office of Science and Technology Policy works to harness sort of the power of science and technology to help America achieve its greatest aspirations and bring new possibility to its people. And of course, quantum is one such technology that will hopefully bring promise to both America and our partners. So now quantum is still early in its development. There are many hurdles ahead of us. Quantum really does have the promise to offer future benefits to our society. And I very much look forward to seeing how in the next few years, quantum sensors start to lead to real world applications, lead to things like better imaging, better PNT sensing. Quantum computers have the promise to allow us to hopefully one day design better drugs or other materials. Now, and of course, though, future quantum computers do carry risk, right? So as we work to develop quantum computing, we do have to always keep in mind that we balance, how do we continue to promote quantum while also being mindful of the, the risks of quantum technologies. So I'm here today as the part of the National Quantum Coordination Office. Now, there are many people in this room I know and many people that I don't. So let me start a little bit by introducing what is the National Quantum Coordination Office. So the National Quantum Coordination Office came into existence back in 2018 with the passing of the National Quantum Initiative Act. The National Quantum Initiative Act showed the importance of taking a whole of government coordinated approach to quantum information science and really reflected the potential promise for quantum information science. So our role is to sort of coordinate quantum information science activities across the federal government, industry, and academia. We perform public outreach, coming to workshops like this and many other workshops. And we also promote access and early applications of quantum technologies. And we also provide expertise to agency missions and industries. A feature of our office is we are actually all practicing quantum scientists on details from other agencies. So we're a small office. We have anywhere from 3 to 5 people at any given time. And I myself am on detail from the National Institutes of Standards and Technology, where I'm the co-director of the Joint Quantum Institute. So I'm a practicing quantum scientist by training in my day job, as I like to say. And everybody in our office are quantum scientists on detail from other agencies that are working within quantum information science. Right now, we're a small office. We have 3 people. Myself, we have somebody from DOD and somebody from the IC community. We typically also have detailees from NSF and DOE. And we're not all physicists. I myself am a physicist, but I respect there's other people within quantum information science. We have mathematicians, we have computer scientists, which reflects the diversity of the type of people that are starting to work within quantum information science. And also, I think this is really important. It's important to have subject matter experts involved in these conversations because quantum is tough. And also quantum is at a very different stage of its development than something like AI. So I think it's important to make sure that, we have the right people in these conversations as we work to promote and advance quantum information science. Now, as I said, the NQI very much takes a whole of government approach to quantum information science. The US has taken a science-first approach to quantum information science. Now we're 5 years into the NQI Act, so there's no question we're starting to sort of evolve that science-first approach. I think it's important to continue to focus on science. There's a lot of fundamental work left to be done in quantum information science, but there's also been a ton of progress in the last few years, and we are now starting to see the fact that, the path from lab to market is getting shorter, right? So I'd like to say now that, we're starting to take a science plus approach, right? We need to continue to focus on science. We're also starting to think about the types of engineering and how can we actually start to translate these to market and really start to have conversations like this where we start to think about what are going to be the end use cases, particularly for agencies and their missions. Now, in addition to creating our office, the National Quantum Initiative created a number of other authorizations for other agencies. Now, I say, the National Quantum Initiative is very much a whole of government approach, but the NQI actually only had authorizations for 3 specific agencies, NIST, the NSF, and DOE. For NSF and DOE, it created 10 new quantum information science centers. Now, the NQI has been amended by other legislation since, including the NDAA. There are also DOD centers. There's 3 DOD-focused quantum information science centers. Now for NIST had the authorization to stand up a industry consortium. I think there's some QEDC people here today. John, there you go. I knew you were going to be here. So essentially, the Quantum Economic Development Consortium was stood up with the support of NIST. This is an industry-led consortium. And then in addition, we have 2 national science and technology subcommittees focused on quantum information science, which I'll talk about in a minute. And then in addition, it created a presidential advisory committee, the National Quantum Initiative Advisory Committee, that can provide advice to the president on how to advance and promote quantum information science. And, essentially, enhance the NQI legislation and the NQI bill in the future. So as I said, we have 2 NSDC subcommittees, but we also have a number of interagency working groups focused on science. Let's see, these days, the different working groups spin up and spin down depending on what's important or, what is most relevant to the time. In the past, we've had working groups focused on science, end users, quantum networking, sensing, workforce development, so a number of things. And essentially through these, both the subcommittees and these interagency working groups, we now coordinate across 25 federal agencies, which again throws you the breadth of agencies that are interested in quantum information science. Now, all of these agencies are interested in quantum for very different reasons, right? Some, like the NSF or the DOE, are essentially funders of fundamental quantum science research, or DoD, of course, right? Some, like NIST, are actively engaging in quantum science research, or of course the DOE labs. and similarly DoD service labs. And then others are potential end users, right? Such as the DOT, DHS, DoD. So essentially, we really have agencies across the spectrum, and also many are thinking about workforce development. So it really does show you the breadth of agencies that potentially will be impacted from quantum information science. And essentially through this interagency coordination, we very much look for gaps, synergies, and ways that we can start to accelerate technology transfer and training. So ThankYouI is 5 years old. We're hoping it'll be reauthorized. We'll see. But I will say quantum information science very much continues to be a national priority. So I'd say our national policy, we typically break up into 3 big buckets. One is continuing to make sure to get the science right? So how do we do that? One of the ways we do that is through these new quantum information science centers, which have been stood up. There's now 5 DOE centers, I said, 5 NSF centers, the DoD centers, and essentially through these, they have partnerships with many universities, many DOE labs, and industry partnerships are encouraged in all of these centers. Now, the second pillar is enhancing competitiveness. Now, how do we do that? Well, one of it is through things like the QEDC, right? Essentially having an industry-like consortia. The QEDC also has a number of its own working groups focused on things like end-use cases, workforce, things like that. And another thing, essentially, is international cooperation, right? For all of the attention quantum gets, in many ways, it's still a very small field. And international collaboration has always been important and will continue to be important in quantum to make sure that we sort of work together to advance this technology as quickly as possible with our like-minded partners. And that brings us to enabling people, right? A big issue in quantum is workforce development. We don't have enough people. Now, in my day job, I'm a quantum scientist, and these days for academics, it's incredibly hard to get postdocs. Why is it hard to get postdocs? Because they're getting great jobs with quantum industry. That's a lovely thing for my students and postdocs, but also means that, I'm not getting the postdocs I need, right? And I hear from industry that they're also not necessarily getting the people they need. So we really need to start thinking about how do we grow the workforce and also get the right kind of people. While I think it's a great thing to get a PhD in physics, those aren't the only kinds of people we're going to need for the quantum workforce. We're going to need computer scientists. We're going to need more people working in microelectronics. So thinking about workforce development is something that's really important to us. And finally, while the full range of applications for quantum computers is still unknown, we do think they will have great promise to drive innovations across the American economy. And another thing I want to make sure to mention is that, because it's very important, I think, for this meeting, and if you look at who's here today, while quantum computers get most of the attention, quantum information science is very much an umbrella of technologies, all of which with different timelines and scales and applications. In addition to quantum computing, it's also very important that we don't forget about quantum sensors or quantum networking and other quantum-enabled technologies. And while the timeline for quantum computers is still a little uncertain, I think quantum sensors are a great example about how sustained federal funding leads to new applications, right? The US has been funding quantum sensors for decades now, 50 or 60 years, or longer, depending on how you count. And quantum sensors really are at the place where we're starting to see them transition to market. So as I said, one of the things our agency does is we coordinate and look for gaps. And of course, not surprisingly, we write documents, lots and lots of documents, which you can all find on quantum.gov if you're interested. And a couple of years ago, in March of 2022, the Subcommittee on Quantum Information Science published a report on bringing quantum sensors to fruition. That report called out the importance of having potential end users, such as the DOT, to identify the relevant quantum technologies and investigate, with dedicated efforts, in partnership with R&D leaders, how they could develop those end use cases. So that's why this workshop is so important, to take sort of those first steps in engaging end users so that we can start to share information and really look to explore, where are the places that quantum technology is really going to add value to agency missions. And that's one of the reasons I'm so excited to be able to see you all here today and talk with you today and welcome you to this workshop. Establishing partnerships early in the R&D process, even though there's still hurdles to be overcome of getting these technologies from lab to market, is really important for helping us to sort of recognize, where the great possibilities are. And I think will help expedite it. It's very important that we have cooperation between industry, academia, and agencies to help facilitate, the science and engineering that needs to get done so that we can really have a shared vision for bringing these and having co-design and bringing these prototypes to market as quickly as possible. So I'm really glad that the DOT is having this workshop today, that we can start to have these conversations, see what are the end use cases, how can we work together to accelerate the progress of those end use cases. So I will say, given all of the recent progress and how quickly evolving this field is, this is very much an exciting time to not only be in the NQCO, but a quantum scientist. So I'm very glad to see so many people here today and online. to talk about, what promise quantum technologies may have. And with that, thank you so much.
Thank you, Gretchen. We are so excited. So I really welcome you all today to join us to this amazing event. There we go. So that was Gretchen and Cordell. And now a bit of our introductions and what's coming up today. So a little bit of me. My name is Prachivakaria. I'm with an agency called ARPA-I especially, and it's modeled after DARPA. DARPA gave us the internet and GPS and Wi-Fi, and ARPA-I hopefully can give you at least a fraction of that as we look towards improved infrastructure and infrastructure of the 21st century. Along with me, my colleague Dan Lemestre from HAS is our co-host today.
Hi, it's wonderful to be here with you today. You heard already about the threats and the opportunities for quantum, and then why this is the right time for us to have a workshop. I don't think we could have had two better keynotes to set the tone. So extremely excited to be here. Thank you all.
So the agenda for today, we will have two brief keynotes, 15 minutes each, from two amazing speakers shortly. Thereafter, we are going to get into what is quantum computing. I already see from the virtual session there are questions coming in. So to help you answer that question, we are going to have a great presentation from Yaakov in the afternoon, and then an amazing panel discussion. And similarly with quantum sensing, what is really quantum sensing? What are the applications? Thereafter, we'll break for lunch, and then we'll come back. We'll have breakout rooms in a room across from here. So not this one, but there's a breakout room just across the table, just across the corridor, and we'll have tables set up so everybody we can start the afternoon times. And at the end, around 3:30, 3:45, we'll have readouts, and we'll call it a day around 4 p.m. and there are drinks afterwards. If you need restrooms, there's a restroom. If you take a right from outside the hall and then keep walking, there are directions everywhere. And we'll have water and a few snacks outside. This is a government building, so we can't have, there's no fresh coffee for you all, but we try our best. At least there's some water and a few snacks here. All right, any questions? One other thing for lunch, again, this is a government facility, so we couldn't bring in catering too easily. So I do recommend it for all of you who haven't ordered lunch already, if you go to Potbelly and order your lunch, we'll make sure to bring it outside and we could all have lunch later today. All right, everyone is all set. So why don't I hand it off to our next speaker? Like I mentioned, DARPA has had a tremendous effect on the transportation sector, from inventing GPS to even the automation sector itself. It was the DARPA Grand Challenge in 2004, 5, 6 that really created the sector. Stealth technology, drones. So DARPA has been investing in quantum technologies for a number of years. And to tell you more about them, here is Dr. Mukund.
So my job this morning is to give you a very brief introduction of quantum technologies across the board, especially from a DARPA perspective. Obviously, that's a big ask and to do in 15 minutes. So here are the few things I want to accomplish within the next 15 minutes. I want to give you a snapshot of how DARPA as a DoD agency approaches quantum technologies. What are the success stories that we would say have gone from lab to actual mature technologies? What are the challenges that we are still working on? And how the DOT, for instance, as well as other consumers of quantum technologies can get involved at this stage to both leverage the success stories as well as to help facilitate the transition of other technologies, which are perhaps more nascent, like quantum computers, from laboratory scale research to actual applications. Okay. So a bit about DARPA. I mean, Prachi gave a pretty brief, succinct introduction to DARPA. Apart from the kind of things that DARPA is known for in terms of the actual mission, DARPA is a DoD agency whose kind of very broad mission is to create strategic surprise for our warfighters and to prevent strategic surprise by our adversaries. And a bit about myself. I'm an atomic physicist with a research background in quantum sensors and quantum simulators. So in fact, actually, Gretchen and I shared the same PhD advisor, and we overlapped very closely in graduate school. So it's still which again kind of comes back to Gretchen's point of it's still a very small community, and we need more people involved in quantum technologies. Okay, so is that a question? Perfect. One of when I was approached by the DARPA leadership to say, would you like to come to work at DARPA for a few years, create a few quantum programs and quantum technologies? One of the big kind of concerns, in a certain sense, within DARPA was, quantum technologies, for all its promise, for all its kind of potential disruptive or even transformative capabilities, still has a lot of hype, still has a lot of misunderstandings of what is mature, what is possible, what is not possible, and so on. And what we really need in part is to tackle the substantial challenges of getting from lab to bench, but also address the hype and distinguish hype from substance. So here are a few snippets of the broad kind of landscape of quantum technologies. While quantum computing does get justifiably a lot of attention, the reality is that quantum sensors, I would say, are far more mature, and that is a opportunity that one should not ignore, especially from the end user perspective, and especially if you take a step back and say quantum systems as a kind of a gentle concept evoke a picture of something extremely fragile, extremely ephemeral, extremely sensitive, and tiny. Each of those can be true most of the times. They can also not be true. But the fragility and the sensitivity of quantum systems is precisely what makes them such good sensors for a whole range of applications, including communications, detection of very, very faint electromagnetic signatures. I've indicated, kind of something that a technology that is kind of rapidly coming to the fore, which is Rydberg-based electromagnetic communication systems. Okay, and these are, very soon we should be able to envision a tiny cells containing room temperature vapors of atoms that can sense radiation all the way from very low frequencies, such as used in maritime navigation signals, all the way to the millimeter wave. Okay. Which obviously has huge disruptive opportunities. And indicated on that coin are a couple of these vapor cells. Okay. PNT, atomic clocks are by far, while we take GPS for granted as GPS functions based on atomic clocks, there are far more capable atomic clocks that are emerging into the market. Shown here are a couple of units, one on a ship in a recent field exercise, as well as one in the back of this SUV. Each of these can sustain local area networks with timing precision even better than GPS for several days, weeks, or even months on it. And for secure, robust timing networks and all the things that from financial networks to navigation to communications that we implicitly rely on timing. This is another technology that I would say is reasonably mature and getting even more robust. And lastly, quantum computing, of course, which I will elaborate on some detail. And from a DoD perspective, each of those areas is the focus of intense effort. In terms of sensing, we have programs across the board, or what we call DC to daylight, electromagnetic awareness across from very, very low frequency magnetometers all the way to millimeters, visible infrared detectors, visible radiation, X-ray detectors, and so on and so forth, all capable of extraordinary levels of sensitivity and precision. Quantum computers, it's still, so comparatively more nascent stage of maturity. Here again, and I will elaborate on this a bit more, but one of the key opportunities and one of the key challenges here is to kind of understand the quantum technologies, not just from the perspective of what is it, how does it work, but also what is it good for. There is, it is simplistic to just say it's quantum, so it's better, it's faster, it's cheaper, it can leap tall buildings with a single bound. That is not the case. Okay, and much of our challenges, much of the work that we do is to understand these quantum systems at a level where we can say, here are the particular applications or here are the particular opportunities where quantum truly yields a disruptive advantage. And given that reality or given that understanding, how do we then take these technologies or take these concepts and transition them in a viable manner from lab to end user? And that is still an ongoing challenge. It is not always the case that a quantum system is better than its counterpart, than its classical counterpart. Once you factor in performance, once you factor in operability, once you factor in cost, once you factor in swap or kind of and kind of robustness and so on and so forth, it is indeed a challenge to say, where are the opportunities, where are the applications, and that is one area where end users, the customers, have a huge part to play in bringing us applications or bringing us transition opportunities to say, can you do this? Or we need this problem to be solved. Does quantum have a solution? And lastly, position, navigation, and timing. Again, these units are getting smaller and smaller and more robust. I would say this is something that is well on its way to mature technology. So quantum mechanics as a whole is old. It's more than 100 years old. So why now? Why are we talking about quantum technologies now? And so to understand that, we also have to understand the performance. If you come at it from a pessimistic approach, you would say any of these quantum technologies, if you compare the commercial state of the art versus the best in class laboratory state of the art, there are orders of magnitude difference in performance. Okay, that is a challenge, but that is also an opportunity. How do we achieve performance, quantum levels of performance, or the limits of fundamental physics in a meaningful package, that would be relevant to the end user? Okay, that is a challenge. Scalability and transition. How do we bring alongside the quantum systems? If you look at any of either Gretchen's labs or my labs, it's 5 foot by 10 foot optical tables filled with electronics, filled with optics, filled with lasers, and so on and so forth. And 99.9% of what we call quantum system is still classical. And the lasers, the optoelectronics, the microelectronics, and so on, that has to be brought alongside the quantum technologies to be able to say these are viable technologies. That is still something that is ongoing, and that is still something we put a lot of effort into. It's not just enough to focus on the quantum system. We have to think about the whole package, about the classical infrastructure and the control systems that go alongside, and how do we develop those and how do we test those. And lastly, like I said, what are the disruptive application spaces? And so why now? Because especially over the past 20, 30 years, the level of quantum control, or the level of control that we can exert on these quantum systems, has grown by leaps and bounds. All the way from one atom or two particle quantum properties like entanglement to very large, and by very large I mean millimeter scale or even few millimeter scale systems that still exhibit quantum behavior, and indeed the first time you see it indeed seems magical. And along with that increasing control or increasing sophistication of control techniques is matched by the kind of expertise in nanosynthesis, microelectronic engineering, nanoengineering, and so on and so forth. So the confluence of kind of the quantum systems themselves getting larger and larger, from the subatomic to the mesoscale, and the microelectronic or the nanoelectronic capabilities getting smaller and smaller, means that we are now at a very opportune time where we can really think about mesoscale quantum systems for a range of applications. And so the way we are thinking about it within DARPA is all the way from the foundational concepts of how do we think about quantum systems in a manner that is application oriented, to all the enabling technologies that have to go hand in hand with the quantum systems so as to actually create something that is actually useful, and finally the application space. So here are a few snapshots, again DoD relevant snapshots from some of my own programs, for instance. Electromagnetic sensing, I mentioned that these quantum systems can be extremely sensitive to radiation, all the way from low frequencies to the X-ray, and infrared imaging is a huge opportunity where these kinds of sensors can be used everywhere from detecting stresses in materials to long standoff carbon, greenhouse gas emissions, and so on and so forth, to create extremely sensitive spectroscopic or spectrographic images of all kinds of electromagnetic signatures, including those from chemicals that we want to detect. Communication systems and sensing. Does this work? Okay. Oh, sorry. These vapor cell magnetometers and electrometers I think, can genuinely disrupt the way in which we think about communication, and that's in terms of secure communications and robust communications, and a range of new materials that are aided in part by our increasing sophistication of quantum simulators as well as quantum computers to actually go after new kinds of materials with novel properties that can lend themselves to far more robust kind of manufacturing processes or indeed new kinds of chemistry. Quantum computers, again, this is, I would say, a slightly more nascent technology, but again, some DoD relevant examples. We are not yet at the fully universal fault tolerant computing era. For those of you who are aware of, we are still, I would say, at the so-called NISQ era, or the noisy intermediate scale quantum era, where the current quantum computers have to work side by side with classical computers, like indicated in that image over there, where a quantum computer, which is extremely good at finding its lowest energy state, can be lends itself to encoding various optimization problems, such as the design of, or the potential design of, resilient networks, where you place antennas, where you might want to place EV charging vehicles. That map of Massachusetts there with the various dots, each dot there is a single qubit or a single quantum bit encoded within a single rubidium atom. And those glows there, and those atoms, by the nature of their quantum interactions, in principle, give us the best design for the optimal design for where you might want to pick and choose or place EV charging vehicles. Similar ideas ultimately it's an optimization problem with certain costs attached to it, certain end goals, and so on and so forth. And so we are still at the, I would say, while these are very compelling initial demonstrations, there is a long way to go, but a very promising road ahead. And so perhaps the most important slide in the context of this workshop, how can the DOT get involved? And so there is, like Gretchen indicated, there's a very large landscape of funding agencies. DARPA is just one of them. And if you were to start all the way from foundational research, the kind that the NSF or the NIH would fund, all the way down to actual commercial technology, where the government should and often does say we don't need to be involved anymore. There's an entire spectrum, all the way from an NIH level to the DoD, various DoD laboratories. And one of the few agencies, DARPA included, have a rather difficult job of being able to identify disruptive concepts all the way from foundational research and try to take them all the way to a deployed technology. And this is where end users or potential end users like the DOT can be involved in coming to us and saying, here's a actual need that or a problem that we are trying to solve. How do we identify faults in kind of load-bearing structures before they occur? How do we design EV vehicles or EV charging stations in a manner that's most cost-effective? How do we secure extremely essential infrastructure like airports? How do we guard against, say, GPS spoofing or GPS hacking? These are the kinds of problems that we would love to be able to insert into our program metrics or structure our programs to say, here's the concept, but here's the problem we're trying to solve. And when we do solve this problem, there is an interested customer. And we want these interested customers to work alongside us during the program to say, well, that's not very useful, or yes, that is indeed useful. Like I said, identifying the disruptive opportunities and the disruptive applications or the transformative applications is still one of the biggest challenges and the biggest opportunities in quantum technologies. And that's where I think workshops like this can really kind of initiate the conversations and hopefully kind of blossom into something that is a very fruitful collaboration and accelerate the transition of quantum technologies from promise to reality. Thank you again.
Thank you again. All right, now it is my pleasure to introduce our next keynote speaker, Rob Hovsapian from the National Renewable Energy Laboratory. Rob, I'd like to hand it over to you. Here, all you need to do is to...
Good morning, everybody. My name is Rob Hovsapian. I'm a senior research advisor at NREL. I'm going to give a little bit of example of the evolution. How do we went from the computation from classical computing to why we're doing the quantum computing, and just give a parallel between the classical computing and give an example of what are the kind of things or problems that we can solve with respect to transportation. So if we look at the evolution of the computation, in 1930s, there was a Claude Shannon that wrote a master dissertation that talked about how do we take a relay and tie it to the electrical systems and be able to do computation with it. So from 30s, from that master dissertation, a lot of the technologies that evolved, so thanks to the space race and eventually the lot of the work that happened in the aerospace industry, that a lot of the development happened in the computation of how do we take classical computing to the next level. So there was at the beginning, started with the modeling and simulation. So there was a lot of work that was developed early from at the TRW, for example. They developed the database, relational databases for with the colleagues from LBNL, and they developed I worked at TRW at that time, so we took the actual relational database that developed for aerospace industry, and from there it eventually evolved that TRW became that they did a lot of the financial analysis, for example. So it kind of started from the aerospace industry, relational databases, and that it evolved even more over the years. And then eventually, once we understood more and more, and we got the computation of the systems more accurately, and we'll be able to do modeling and simulation much better. The next thing our systems became more and more complex. We wanted to add more and more things to it. So at that time, DARPA started a program called Sidecars to Factory in the 90s, late 80s, early 90s, where they wanted to go ahead and look at it. How do we bring in the design to manufacturing? How do we actually bring in hardware that from a manufacturing that actually ties to the computation? That kind of started a lot of, we see a lot of the 3D printing today's, and and a lot of that computation methodology and the system that was developed was started as part of the DARPA program in the late 80s, early 90s, and then eventually with the automotive industry and then Department of Department of Defense got into more of doing the actual, how do we bring in the hardware in the loop and power hardware in the loop techniques. So the Navy started the program that said we want the modeling to be our simulation. So instead of going and designing or building a Navy ship, we want to be able to do hardware in the loop and power hardware in the loop. So a lot of the digital twin and the hardware in the loop and power hardware in the loop techniques, and that's still evolving. That's the state of the art today. But we're doing the actual hardware. So taking it from that next steps from hardware in the loop and power hardware in the loop, emulating the real system, the next thing is we're generating massive amount of data. So can we take that massive amount of data and how we develop the relational database and the systems in the 70s and the 80s and tying them together is becoming more and more complex. Hence, there's a need for, is there a way that we can look at the quantum approach, that we can look at the unformatted data? Can we take the data that we're generating, the massive amount of data today, and put them in a relational database and finding out the optimum solution? I think somebody earlier said that this is optimization problem. We can, but it takes a massive amount of effort to do that. So in order to be able to observe the data without creating a lot of the formatting and insertion, and be able to observe the system and come up with a solution, it has hence the need for the quantum computing. I mean, today as a human, when we're sitting in the room, we don't go look at the digital thermometer and say the room is hot or cold. We have a bunch of sensors in our body that kind of makes that determination for us. So it's the nature's way of coming up with a determination solution. The same thing we want to start using the quantum computers to do that. And then I'm going to come back and talk about a little bit about how tying it to use cases for the transportation. So what we're seeing is massive amount of growth in the systems that are interacting. And so whether it's electrical vehicle talking to the weather station or talking to your home management system, so there's a massive amount of systems that are all interacting and talking to each other. So since the last 5 years, we're seeing 9x growth of the controllers and the systems that are talking to each other, and they're all generating data. So when you have 4 or 5 systems talking to each other and you're collecting the data, populating a relational database or in some kind of a system and come up with an optimization, I'm not going to say it's easy, but it's a doable thing to do. But when you start taking it at thousands of systems or even eventually millions of the systems that are all somehow related to each other and interacting with each other, it becomes a way that we need to have a different ways of thinking to do that. And in order to do that, that complexity of system, so this is digital twinning approach that we're looking at right now. So this is the hardware in the loop and power hardware in the loop approach, where we do a lot of emulation. So we go away from a modeling and simulation. We capture more of the emulation of the real-time systems or actual hardware of the system or control of the system, and come up with the observability of the system. But that's today's technology. That's the state of the art today. But as we expand this more and more, and we start looking at the thousands of the vehicles or millions of the weather stations that are communicating with each other, it's going to require different ways for us to do that. So that's the evolution. And what we're doing is what we're seeing is the complexity in the system. So if we have system that's the technology is not sophisticated and the communication methodology is, as we see today, it's doing in a classical modeling and simulation is okay way to do it. But as we get more and more complex, looking at the top right side of that figure, where it becomes more, the technology becomes more complicated and the communication methodology becomes more complicated, it requires more of a emulating and actually bringing in the hardwares together and looking at it. So today at the national labs, we're looking at 600 of those systems tied together, but ultimately we want to look at the thousands of those systems that, how do they interact with each other? This could be electrical vehicle, it could be an aircraft communicating with a weather station. So how do you bring all those systems together that at a thousands of level? This is again in a hardware in the loop and power hardware in the loop techniques. But as we generate this massive amount of data, is ability to understand how do all those systems interact with each other. That's where it becomes more and more complex. So if you want to look at the evacuation event that's happening, like a hurricane hits the East Coast or an earthquake in the West Coast, and you want to issue an evacuation, it's like, can we solve those problems based on all the electrical vehicle or the hybrid vehicles out there? We can, but that becomes insane amount of computation powers that we need to be able to do that. So understanding of how all those things are related and coming up with more observability and solution for those systems. So in order to understand that, so what we talked so far about the state of the art today, which is on the digital real-time simulation side, massive growth, and then the quantum computing that doing more optimum computational for us or optimization for us together. The piece that are missing is massive amount of data being generated. If we put a computer scientist together, they can take all that data, populate in some kind of system, and find a solution or optimization for it to it. But it's becoming more and more complex to do it. And sometimes we want those decisions very quickly. We want to do that observability within a second or minutes in order to make it's decisions of how to either optimum evacuation route or a decision on taking a different approach. So to do that, it's going to require a way that we can tie this together. So we at NREL, not a computer scientist, or I'm not a quantum person, but I'm an applied person. So how do you bring in the applied system and use a solution for quantum type applications together? And how do you tie them together? So and in order to do that, I mean, we work together with our colleagues at the quantum world and as well as the colleagues from the real-time simulation side, and said the need is for us to be able to put these things together. And as a result of that one, what we developed is with atom computing, which I think they're presented here today, and real-time simulation modeling companies, and we develop what we call the quantum in the loop. How do you take a actual hardware, so create a real-world environment, run a quantum optimization, and validate it in an environment that as close to the real world, and be able to optimize that before you take it, basically taking the risk away from taking it the next level. So that was the quantum in the loop. We developed it last July, and now we're looking about actual use cases and applications that we can use that for. And I'm going to give an example of kind of application. I'm going to make the applications to be more of a transportation-centric. So looking at this quantum, I mean, we can identify pattern much quicker than we can. I mean, not that we cannot do it today, but it takes a massive amount of computation to do it. But if we want to be able to observe it, identifying the pattern much faster, more secure way of communication. There was a discussion earlier where we talked about the GPS versus atomic clock type sensors. So how do you tie all those things together? And this is one example. So we rely more and more, whether it's our electrical vehicle or our aircraft or our black boxes, they all use GPS clocks. And if there's a way that for some reason we lose that GPS clock, what's an alternative for it? So coming up with a way, and this is a low-hanging fruit that we can do. A lot of work has been done in the past with atomic clock. Can we be able to operate in both environments, both the GPS clockwork and as well as atomic clockwork and tying them together. So if an events happen, can our system be smart enough to be able to switch from one to another and survive those events and then recover from it? So that's one use cases that we're working closely with Atom Computing team members and our colleague at NREL to put that together to be able to do ability to do that. The other use cases we're seeing more and more, as example came earlier with our colleagues from DARPA, that's how do we want to do EV infrastructure planning? So as we add more and more EV, what are the congestions for the grid, or especially when there's an events happen and the seasonal events? So how do you do better planning for the electrical vehicle optimization? So it's a true optimization type solution that we can use quantum computer to do that. The other thing is that part that I'm more excited about is the evacuation. I live in Tallahassee, Florida, and every time we get a hurricane event that comes in, I mean, everybody gets on I-10 or I-75, or there's like the congestions happen, and it's not that the state or the Department of State doesn't know how to do it. It just when a weather pattern happens, you want to make sure people are safe. But today we have a lot more electrical vehicles. We have a lot more vehicles that are hybrid vehicles. So be able to do more intelligent evacuation based on the event, looking at the weather information, the traffic information, the state of the charge of the vehicles that you're issuing the evacuation to, and issue more intelligent evacuation to the people doing it, both from the transportation perspective as well as the safety and weather information. So tying the weather information more dynamic, more real time. So this is a true problem where a quantum can shine doing this. The other one is there's a lot of dependency within the transportation. I mean, when an emergency event happens, whether it's keep mentioning a hurricane, but also whether it's a winter storm or a earthquake, and you want to issue those evacuations or safety, there's the road and transportation also depends on the communications, also depends on the power grid. How do you bring all those things together and come up with an optimum way of doing that? So those are the kind of problem and challenges that quantum will shine doing it, and those are the kind of things that we can do it, start doing it today. Getting those problems more in the hand of the PhD students and the academia to start planning those, working with the quantum vendors to start validating those, and the ability to be able to come up with the solutions to do it. That's my last slide, and look forward to our dialogue and the discussion. Thank you for inviting me.
Against each other, as well as what's currently available now versus classical and how those work?
Excellent question. Actually, that's the quantum in the loop that we did with IEEE. That's we took very simplistic system, 4-node grid system. When a failure event happened, how quickly you optimize it to demonstrate that we can run it in classical computing and we can run it on quantum computing and compare them together. But that's a benchmark test. Is what we really like to do is take those and do it more applied to a transportation sector evacuations to do it. But starting at a small use case, validating the approach, but comparing it to the classical computing is the right way to do it.
Okay, thank you.
Please.
I'm curious if you've integrated any like social considerations in terms of optimization for like EVs, for example. I know there's a lot of discussion about the equitable nature of deploying EVs. Is there any room for integrating like equity considerations or other?
Yeah. Have we done it? No, but is there a room for it? Absolutely. If you can mathematically represent the social behavior and incorporate that in the optimization routine, absolutely, yes.
Got one more. Hi, I'm Bill Markville at MAA. Considering airspace management, traffic flow management, air safety, and so forth, that's very important, especially when weather impacts air transport.
Absolutely.
Has that been analyzed or at least considered in your approach?
We have not done it, but we're taking the example of transportation for vehicles, but that's same thing could apply for aircraft as well, especially when you tie it to the weather and you tie it with other events. Yeah. Because that's a good example where you have to make a decision very quickly. I mean, in aircraft cases, I mean, I came in from the Northrop Grumman F-22 avionics programs where a lot of things, so understanding making that decision very quickly, it's important to do. I mean, where in vehicles, emergency, you got to do it in minutes or hours. where in FAA you have to do it in seconds or in some kind of minutes, otherwise you missed it.
Correct.
Yeah.
Thank you. Will you be around for the workshop? Yes. We'd love to forward.
That's come up with a formulating a use case from it. Yeah, absolutely.
Okay, thank you, Rob.
Thank you.
All right, so next you've heard the premise of quantum computing, but what does it actually mean? So this is where I invite Yaakov Weinstein to give us a quick 15-minute presentation, very quick, 15-minute presentation and overview of what exactly is quantum computing. And then I have Thomas Ward from IBM. Now they're one of the first ones to start working on quantum computers. Phil Lotshaw from Oak Ridge National Lab. Oak Ridge is really interesting that not only do they have the most powerful HPCs in the world today, but now we can also start comparing them to quantum. So we're really excited for Phil to be here. Franz Klein. Franz runs QLab, which is a shared laboratory space, and he'll tell you more about it at University of Maryland. And then Allison Schwartz from D-Wave, and they've been doing really amazing use cases and in the sector as well. So tell you more all about it, and where is quantum computing today? What does it actually mean? And what are some of the applications? We have an exciting panel for you. So over to you. And everybody's presentation.
Yeah. All right, thank you, Pachi. It's really a pleasure to be here. Thank you so much for taking the time and taking the opportunity to learn about quantum. I hope you find this an exciting day. We've got some great things to go on. It's certainly quantum computing, and I'm really honored to be able to start this conversation. So I want to really take a moment to look a little bit under the hood at what is a quantum computer, talk about some of the jargon, some of the terms that you might hear from some of our speakers or when you go out into the larger quantum world, just to try to hone in on some of that so that people will be educated. I always have to go back to my advisor when I was an undergraduate, my advisor at NASA Langley Research Center. He actually just retired at the age of 80, having published, continued to publish for a long time. This is not a quantum Gretchen, it's nobody that you know. And he told me, if you want to look smart, just say the right word. And his particular word was diffraction, because that's what we were doing in material science. So that's what I want to teach you all. At least to look smart, to know what questions you might ask. We have wonderful industry people here. You should ask them questions. Okay, so let me start. What is a quantum computer? So a quantum computer is a computational device based on qubits. The qubits are going to be the quantum parallel to bits. So everybody knows what a bit is. They're in all sorts of computers that are in front of us. They are little things, we don't care what things they are for the moment, that can be either in a state 0 or in a state 1. Okay? And qubits are the same thing, except they're little quantum devices that can be in the state 0 or the state 1, but because they're quantum, they can also exhibit different quantum phenomena. Okay? And the two phenomena that we're going to just talk about quickly here are superposition and entanglement. Okay, I'm asking you to take this on thing. Okay, for those who are not familiar with quantum. Okay, the superposition is the ability for quantum systems to be in multiple states at the same time. So while your classical bit is in the state 0 or in the state 1, your quantum bit can be in the state 0 and the state 1 at the same time. Okay, does everybody believe me? You shouldn't, but this is true. It's 0 and 1, and it is not 3 states. It's not your state 0 and state 1, and state 0 and 1 at the same time. That is not true. Okay, what actually happens is that the qubit can be anywhere in between 0 and 1. It can be a little bit 0 and a lot 1, or a little bit 1 and a lot 0, anywhere along that continuum. And there's also a phase. Okay, so you can imagine your states are like a sphere, and the state of your qubit can be anywhere on this sphere. It's here 0, here's 1. The state of your qubit can be anywhere here, anywhere here, anywhere here. Okay, it can be anywhere along that. That is superposition. And that inherently gives a quantum computer, which controls our qubits, an inherent massive parallelism that doesn't exist in classical computation. Okay, that's number 1. Number 2 is entanglement. Entanglement is the ability for quantum systems to be correlated with each other above and beyond what's possible classically. Okay, so entanglement is a fundamental resource for many things like quantum communications, but also plays a role in quantum computation. Okay, so I want you to keep those things in mind: superposition and entanglement. These phenomenon enable a quantum computer to do things some of which Rob talked about, some of which Mukund talked about, some of which we'll talk about on the next slide. But the initial motivation for it was that a quantum computer has the ability to break modern asymmetric cryptographic codes. That means RSA, or to be very practical about it, when you send your credit card number over Amazon, the reason why, in theory, nobody can read it is because it's encoded. If that person trying to hack your credit card number had a quantum computer, then they'd be able to get it very easily. No one has a fully functioning, what we might call a universal, a quantum computer capable of doing everything that in theory a quantum computer can do. No one has that. However, there's a worldwide race to try to build these quantum computers, and you may have seen some of these headlines over here. IBM is here, their 1,000-qubit system, and Atom Computing is here, their 1,000-qubit system. And then there's also some predictions it's going to be $1 billion industry and $1 trillion industry, and God knows what else. But okay, so those are wonderful headlines. We want to try to be a little bit practical. Okay, let's go. So why quantum computers? Why are you interested in this? And again, I'm just going to expand on what was said before. Let me go backwards actually over here. Number one, what I mentioned, the threat to secure data. Right? The quantum computers could break asymmetric cryptographic protocols, including RSA, including digital signatures. This was really the motivation back in the 90s to start funding from ARPA, quantum computing research, and the algorithm that is capable of doing this. Right? So the quantum algorithm, an algorithm that you run on your quantum computer, is called Shor's algorithm, after Peter Shor, who's the guy who invented it. Okay, so when you hear Shor's algorithm, that is the algorithm that allows the quantum computer to break encoded information, to get into that information. Okay. On the other side over here, we have the capability of quantum computers to more quickly sift through unsorted data. Okay? And that's based on an algorithm called Grover's algorithm, off of Love Grover. Just note, I'm from New Jersey, and both of these algorithms were discovered in New Jersey. So New Jersey's place to be. In addition, quantum computers do other things. Quantum computers can solve certain problems of linear algebra more quickly than their classical counterparts, including solving sets of linear equations. Now, there are caveats on all these things, okay? So you have to be very careful. So I'm just giving you like a taste of it, but there are lots of mathematical caveats to all this. Different aspects of learning the eigenvalues and eigenvectors of matrix, some other things as well with linear algebra, and that has a number of different applications, including optimization, logistics, machine learning, and so on and so forth. The ability for quantum computers to simulate naturally occurring systems, such as materials, pharmaceuticals. Again, so that's why you have quantum computers as a promising technology for the revolution within material science and for pharmaceuticals. And then finally, quantum machine learning. Quantum computers, again, in theory, should they be sufficiently mature, have the ability to perform machine learning using less training, providing more accurate results, and doing so at a faster speed. Okay, so these are all potential applications for quantum computers. Now, how do you build a quantum computer? Okay, so the way you build a quantum computer is by its qubits. That's what you start with. Those are the basic fundamental things within your quantum computer. And the quantum computer's job is that you control your qubits. Okay, so what do you want? What do you want your qubits to be? Okay, well, first of all, they have to be some sort of quantum systems. Well, what keeps a system quantum? What keeps the system quantum? I'm looking at a chair. The chair is not entangled with anything else. The chair looks like it's right over there. It doesn't look like it's two different places at the same time, right? So why is that? And so the answer is, it's another term, decoherence, right? You want to keep your qubits isolated from their environment. What is environment? Environment is everything. It's air molecules. It's anything. It's anything is an environment. And you want to isolate your qubits from their environment. Okay, which you can do maybe by using like strong magnetic fields, keeping things very cold so there's no heat, right? You need to keep them isolated from their environment, because if not, decoherence sets in, which means that your quantum systems start interacting with their environment, causing them to lose, I'll just use this term loosely, quantumness. They are not going to exhibit any more superposition or entanglement because they're interacting with their environment. Okay, and so if you want to look smart, and you talk to these industry people who are out there in the audience, you should ask them, what is your decoherence time? What does that mean? It means how long is it that your system can stay quantum and exhibit quantum phenomenon before it just turns into a piece of junk. Okay? So you need to keep your qubits isolated. In addition, you need to keep your qubits there. Okay, so if you're going to use particles of light called photons as your qubits, guess what? They tend to move very fast. And so you need to keep them in one place. if you're going to take atoms and put them in an atomic trap, you need to keep them there and make sure they don't fall out. Right? So you need to isolate your qubits from its environment, and you need to make sure that they stay put. They stay where they're supposed to stay. You also then, if that were not hard enough, you need to control your qubits. You need to get them to do things like rotate, right, from the 0 state to the 1 state, or hopefully anywhere in between, right? And you need your qubits to interact with each other. Okay, so now this is really a tightrope. Thus, if you want to perform 2-qubit gates, now why do I want to perform 2-qubit gates? Well, let's go back to regular computing, regular normal computation. What are the basic gates in a regular computer? Well, you have a NOT gate. What does a NOT gate do? It turns a 1 into a 0 or a 0 into a 1. Then you have things like controlled NOT gates or XOR gates. And you need bits to know, like in an XOR gates, if you have 0, 0, then the output is going to be 0. If you have 0, 1, the output is going to be 0. If you have 1, 0, the output is going to be 0. And if you have 1, 1, the output is going to be 1. Right? That's your controlled NOT or your XOR gates. Okay, well, how do the bits know like what the other one is? Well, they have to interact somehow. And the same thing is true with qubits. So you need your qubits to interact with each other when desired, but not when not desired, because if you have them interact when it's not desired, then you're back over here. That's bad, right? So you need your qubits to interact with each other and nothing else, and only the qubits that you want to at that particular moment, and be able to turn that off and on. Okay, so that's something that you need to do. And preferably, we like to know how to initialize and measure your qubits. Initialize being set by 0 when you want them to be at 0, and then measure them when the computation is finished. Okay, so these are things that we'd like for our qubits. Now, there are a number of different possible ways to realize qubits. And here are just 3 of them. I'm not going to go through like all the differences here between them, but they're superconducting qubits. This is the way that IBM, D-Wave, Google, and others are pursuing quantum computing. These are just simply little loops of superconducting material. Again, these are materials that don't have any resistance in them, and so current could go through them without any resistance. And we have ion traps, which are atoms in which an electron has been stripped away. So the atom is now charged. If you strip away a negative charge from one of the electrons, your atom is now positively charged. We have photonics, which are photons, particles of light that we can control. And each of them have pluses and minuses and suggest the next steps for what to do. For example, one of the positives about superconducting qubits is you can use similar substrates to what we do for conventional computers. One of the negatives is they have relatively short decoherence time compared to some other systems. Ion traps, we have the advantage of each atom is always the same by definition of nature. However, they have very long gate times. It takes a long time for you to actually rotate them, for example. And you have photonics, where you have minimal decoherence. The photons don't interact with each other as much. They don't interact with the environment as much. However, because they don't interact with each other, it's also really hard to do certain gates. Okay, so each one of these technologies is being pursued by different industry partners and being researched within academia. They all have their pluses and they all have their minuses. And the question then is, how does each one going to evolve as we move into the future? Okay, however, forgetting for the moment what is actually under the hood, what we want to know is how powerful your quantum computer is. What do you do? So I'll just give an example. Like, let's say you wanted to buy a regular computer. Okay, so I should never be in this position. If I have to ever buy a regular computer, I call my wife and I ask her which one. Okay, but if for some reason I couldn't do that, I could look on a website, and the website tells me about like all different aspects about my computer. So for example, it might tell me that this computer is 2.2 gigahertz. Okay, I know what gigahertz is. I know what 2.2 is. I don't really know like how that, it seems to be something with speed. Like for a regular computer, I'm not asking for like the right answer, you can tell me later. Okay, but I have one computer here that's 2.2 gigahertz and it costs $1,000. And I have another computer here that's 2.5 gigahertz and it costs $1,200. Let's just say. All right, so I might say, to myself, well, you know what, 2.5 is bigger than 2.2. And it's $200. Okay, I can deal with $200. So I'm going to buy the 2.5 gigahertz computer, even though it's cost $200. You know what? And if I made the decision just on that number, I'm probably in pretty good shape. Right? I don't actually need to know what a gigahertz is in order to be able to make that decision. And so we like the same thing for quantum computers. How can we evaluate the power of a quantum computer, not having to pay attention to whether it's a superconducting qubit or an ion qubit? I just want to know, like, how good is your quantum computer? And so there are a number of different metrics that one can use. This particular one that I'm using, which is quantum volume, was originally formulated by IBM, and we can see how powerful our quantum computer is. Now, what is in this metric of quantum volume? Well, 2 things. Number 1, the number of qubits. Okay, so everybody likes talking about the number of qubits that they have because it's like easily identifiable. It can go up And like, and you can have like all sorts of newspaper headlines about it. So that's wonderful. Okay, but that's not sufficient. Okay, what you also need is you need to know how good the qubits are. Now, what does that mean? Well, we run our regular computers. Okay, so we might get frustrated with it, and every once in a while we'll see the blue screen of that. But in general, our computers work pretty well. Okay? With quantum computers, it's much harder. And the basic gates, because there is decoherence, because things interact with their environment, because it keeps it very hard to keep qubits isolated, they don't necessarily work as well. Okay? There are going to be errors. Okay? And so what quantum volume does is it tells us how many qubits do you have that can perform how many basic operational gates in a row before it doesn't work anymore. There's mathematical numbers attached to all those things, but in a general sense, if my quantum volume, I'm using the log 2, for example, that's IBM, so I'll talk to IBM person about collide. I'm using log 2 here. Effectively, what this says is that if my quantum volume for log 2 is about 10, then what it more or less means is that the quantum computer has 10 qubits that can perform 10 gates in a row before everything falls apart. Right? And so you can see here, what we've done is we just mapped this out. Here we go, 2015, 2020, 2025. This is just the year. And we can see how much quantum volume has been achieved by different industry players. Okay? And so you can see here circles for IBM, and squares for Continuum, and triangles for IonQ. And you can see like what the quantum volume is again. This is a lot of base scale. Now, in addition to that, on this graph, we put these dashed lines. Okay? And these dashed lines represent different milestones which be important for a quantum computer to achieve. And so, for example, there are a couple I want you to pay attention to, right? Schwartz algorithm, who's remember what Schwartz algorithm is? Crypto, very good, yeah. Right, that's the one that allows you to break RSA light. So this particular line is the quantum volume that would need to be achieved by a quantum computer to break RSA 2048. Okay, so usually when you send your credit card to Amazon, you use an RSA 1024. Okay, this is what a quantum computer would need to break RSA 2048. Okay, and now we can say to ourselves, okay, look, well, let's follow the trend and see how long it's going to be before a quantum computer is going to reach that. Right? And so all these things are similar. So here we have Rover's algorithm, that's one for sifting through data for machine learning. Various things about simulating chemistry. Okay, so that's what all these are for. But we see here two more lines. Okay, this line here is one logical qubit. And what's a logical qubit? A logical qubit is when you've taken your quantum information stored in your qubits, and you've encoded it into an error-correcting system. Okay, so you're using multiple physical qubits to encode your data so that it will be robust against errors. Okay? Now that's very important because we're always going to assume that quantum computers, the qubits, are going to have errors because it's so hard to keep them isolated and like we talked about before. And so I want to be able to encode my data into logical qubits so that they're robust against errors. Right? And we can see that we're just about at the point where we can do that, we as in humanity can do that successfully. Right? However, that is not sufficient for quantum computing to work on a universal level. We also want to be able to encode our data, and then we want the encoded data to be able to perform basic gates because we can't do anything beyond a gate. That's harder. Okay, so we assume, again, this is all approximate, but we assume that in order to be able to achieve one logical qubit capable of performing all necessary gates for universal computation is going to cost approximately a quantum volume of this. Okay, so that's what these lines are for. Okay, so now, with all that in mind, we can try to look at this metric and try to get some picture, some prediction of the future. And so if we simply follow this trend that we see, we're going to be around here before quantum computer is capable of breaking to the RSA 2048. And that's going to be 2055 or so. Right? Now that line, that number is not crazy. There have been other studies that have looked at similar things, much more complex, and they come out with more or less something like that, some number like that. However, if you ask the people in quantum computing industry, and I suggest that you do so, how long is it going to take before you have a quantum computer capable of reaching this? They might tell you 2055, or they might say, no. Once we get error correction working well, we'll be able to go much faster. Okay? Now this line is just completely arbitrary, but we're going to go much faster, and therefore it is true that maybe the current trend would lead you to suspect that you won't have a quantum computer that's working fully until 2055 or whatever it is. Once we're able to actually really control based on quantum error correction, we'll be able to go metrics. Okay? So, but the importance of metrics should not be underestimated. We want to be able to know, we want to be able to communicate how well we're doing within quantum computation. And so, again, so despite this, and despite the difficulty that is inherent in building a quantum computer, we have seen market progress. So for example, we've seen a number of demonstrations of what's called quantum supremacy, the ability of a quantum computer to do something that no conventional computer, even a supercomputer, can do in a reasonable amount of time. Or reasonable, I mean, more or less than the age of the universe. Okay? We've seen a growing number of qubits, both in superconducting qubits, in ion trap qubits, in photonic, we've seen advance into photonic qubits. And here's some of the industry players, IBM, Continuum, IonQ, Atom Computing, PsiQuantum, Xanadu, all of which are pursuing different approaches towards quantum computing. And again, I would like, for them all to report some sort of metric. Some of them do, some of them don't. Some of them report more localized metrics, some of them report more global metrics. And so, that's however, the idea of metrics, I think, is very important. It's something that we should keep in mind. I will note over here, especially since Allison is in the room, that there are other types of quantum devices that can compute that are not universal quantum computers. Okay, that is quantum annealers. And that's what D-Wave built. Allison, are you gonna give a little spiel about?
I'll be up on the panel, so you can ask me questions.
Okay, so you can ask Allison all your questions about the D-Wave quantum annealer. However, these are computational devices that exploit quantum mechanics for their computation, but are not universal quantum computers. And therefore, for example, they cannot implement Schwartz algorithm. Fair, we're good, Allison? I'm not saying they can't necessarily. I'm not saying they can't factor. They cannot implement Schwartz algorithm as. Yeah. Okay. Yeah, we're good. Okay. Okay. So please do keep that in mind. Now I'm going to be here on the panel, so we can ask any questions about that. Okay. We as in the United States, we are not the only ones pursuing quantum computing. Okay? We have allies, and we have not so much allies who are also pursuing quantum computing. And to sort of point that out, Australia just made a very big, very big splash by investing 620 American dollars, 620 million American dollars into PsiQuantum, which is a company pursuing photonics-based quantum computing out in California. In Canada, there's Xanadu, which is also using photonic quantum computing. Somebody's unmuted. Okay. China just recently announced they produced a chip with more than 500 superconducting qubits. Yep, we're good? Okay. I also should note that China has demonstrated quantum supremacy using both a photonic quantum computer, which is this picture over here, and also a superconducting quantum computer. However, at least according to public announcements, Alibaba and Baidu have both reportedly pulled funding for quantum computing. That's interesting. And then in Europe, there are a number of different companies, including ARPA-I, ARPA-I Quantum Technologies, all of which are pursuing quantum computers using different platforms to try to achieve that. Okay, so maybe I'll stop here for the moment and see if there are any questions out there, Chachich. And then these are the questions we're going to ask our panel, so I'll go through them in a moment. But in the meantime, any questions? Oh, I wowed everybody. Okay. Good. Okay. So, how do I go backwards? Okay. So, what we're going to do now is we're going to have a panel. This is okay if I do this stuff. We're going to have a panel for quantum computers. We're going to have a number of excellent panelists who are each going to introduce themselves, and we're going to ask them a bunch of questions. And so you should think up of your own questions as well. But these are some of the questions that we're going to ask them. Why should the Department of Transportation care about quantum computing? Again, thanks to Rob, who's covered a lot of that already. But we want to hear from our panelists as well. What are some of the near-term applications for quantum computing, if any? What is the role of DOT, or what is the suggested role that DOT should play within the quantum computing ecosphere? When will there be something practically useful available for DOT to tackle real-world problems? Why should DOT pay attention to your organization? What are you doing that's unique? Please be positive only, not negative about other people. What industries and government agencies do you see doing? What do you see them doing with quantum computing? Again, that to be tied in with what DOT is doing and how DOT can complement those efforts. And on a personal level, what is your favorite use case? Those are my suggested questions. Everybody should please come up with their questions. I don't know how much time do we have left.
Yeah, we have about 30 minutes.
Okay, so we have some time, and so can we call everybody up here? I actually took it out. How do you want this?
Perfect. If you'd like
You
to
want me
sit
to
down,
sit? Oh, yeah, sure.
that way it's more comfortable. You can have a dialogue. I think we have enough chairs. And then slides are in the order here. So you might want to do Thomas first.
Okay, so we're going to go through our speakers. We're going to allow them 1 to 2 minutes maximum, please, for introduction. That's okay. Thomas, IBM, we'll start with you.
Great. Hi. Pleasure to speak to you all. Thank you for being here. Tom Ward from IBM. I've worked for IBM for about 35 years. Little background on myself. The image that you see here is on the left-hand side, quantum data center. And that image is right beneath, I sit on the second floor in IBM in Poughkeepsie of our quantum data center. There are about a dozen quantum computers that are right beneath me. Interesting story. Remember the earthquake that hit in New Jersey? I was like one of the only people in the office, and I'm like, ooh, this is a little dicey. Those are about the closest to absolute zero of anywhere on the planet, all of them. And so there were no issues. Some of the quantum computers glitched a little bit, but came up quite resiliently thereafter. Our largest computer on the right, these are based on Heron processors. They're about 399 total qubits, 3 of them coupled together. So I won't get too much into it, but we've kind of made the shift from just larger and larger qubits to parallelized computers. And so that's a little bit of information. Next page, just in the interest of time. These are some of the use cases. Take a picture of it. I'd encourage you to. So this is a whole range across the industries. We'll talk about this later. Use cases that may be relevant for you from a public sector perspective. I've spoken to folks in the aerospace industry and others, and you'll see a whole range of both quantum machine learning, optimization use cases, and simulating nature types of use cases that are reflected there. So look forward to speaking to you further. Thank you.
Thank you, Thomas. Oh, yeah.
Hello, my name is Phil Lotshaw. I'm a research scientist at Oak Ridge National Laboratory. I have specific research interests in quantum optimization algorithms, which could be relevant for the Department of Transportation, as well as other topics in quantum physics. Oak Ridge National Laboratory performs a variety of research that is aimed towards advancing national interest in the goals of the Department of Energy. And we have a variety of programs. I'll highlight 2 of them now. One is the Quantum Computing User Program. This is a program where you can submit applications to the lab to get free quantum computer time. So if you have a research project, you want to test out a quantum algorithm, you can submit an application here. It's a way to do it. We also have one of the 5 DOE National Quantum Initiative centers, the Quantum Science Center. In addition, we have a quantum information science section, which includes 3 groups: quantum communication, networking, and quantum algorithms, and computational science, which is where I'm located. Very happy to talk with anyone that's interested.
Hey, I'm Franz Klein. Doesn't matter. Director of the National Quantum Lab at Maryland. It's a partnership between UMD and IonQ, but we are also open to have provide access for other providers. So what we are doing is testing out, benchmarking, and getting, in particular, students and faculty and interested people involved that are not part of the standard quantum information science environment. So examples are over here. So ion trap computers were already mentioned. There are, of course, limitations, like for all computers. So in particular for ion trap computers, is the corresponding long gate timing and also the scalability. Big advantage is simply the all-to-all connectivity of these systems, which allow you simply to do a highly entanglement system within the small number of qubits that you are doing. So therefore, you have these high volumes. Other pieces that I should simply point out. So it was already said that quantum computers maybe in the future you can use in order to deal with very large databases, do searches, etc. I tell you, it's almost impossible to put large data into a quantum computer. So we are talking about a quantum volume, or let's say the quantum probability space, yeah, which is very large. So it's simply 2 powers the number of qubits. If they are entangled to each other, if not entangled, it's actually similar to classical computers. But access to this large probability space is very difficult because this space lives in a complex world. And we are living in a real world. Yeah, so we can only put real data into it, and we can only measure projections onto the real space. In different words, we can only measure small fractions of a quantum computer is really doing at the time. Yeah, please take that into consideration when we come to discussions here. Good.
Hi, well, folks got a little introduction to me. Allison Schwartz with D-Wave. I am not the technical expert. There is a technical expert in the room. So if you have any questions about our technology, I'm happy to send you over there. I do public policy for D-Wave. D-Wave is a company. We have a 5,000 qubit system. It is a quantum annealer, as Yaakov mentioned. It is available in the cloud today. It is cloud access. We have systems in Germany, in the US, as well as in Vancouver. I say 5,000 because, as Yaakov mentioned, there is different talk about number of qubits and what they do. We also have a prototype of our Advantage 2 system, which is a 1,200 qubit. So again, 5,000 versus 1,200. We also had a supremacy result that came out. It's under peer review. Using our 1,200 qubit. And it actually solved an optimization problem in 20 minutes that Oak Ridge's Frontier computer couldn't solve for millions of years. So in that aspect, it's going through peer review now, but there are different ways of looking at it. And we are actually working with a variety of different companies and governments around the globe in looking at optimization problems. And not all problems need quantum computers. Not all problems are best for quantum computers. Annealers, we use a superconducting chip fabrication, as mentioned. All of these different systems are advancing at different timelines. And one thing that we look at, if you want to go to the next slide, is what are the types of problems that we can solve today while our internal hardware teams are working to advance the hardware. So there is actually work that can be done today to solve real world problems. But they're usually done in a hybrid format. So part of your problem can still be solved classically and should be solved classically. There might be a part of that problem that is an NP-hard problem that could benefit from a quantum processing unit. And so a lot of the areas for this discussion today is looking at what are those type of optimization problems, because that is within the scope of a lot of the different technologies here. But with that, I'll pause and Yaakov, we can get into questions and answers.
All right, so let me go back to questions here so everybody can see them. All right, so let's start. Maybe I'll conflate the first 2 questions since people have already kind of addressed some of it. Why should DOT care about quantum computing? And what are near-term applications for quantum computing? And Phil, I'm going to start with you because you are the least practical in terms of building stuff. Go for it.
Yeah, so we don't build devices at Oak Ridge National Lab. So, I mean, I think the reasons that you should be excited about quantum computing are related to many of the things you talked about in your presentation, Yaakov. There's known speed ups like Shor's algorithm, Grover algorithm, that in the future are expected to give huge scaling advantages in terms of solving problems faster than is theoretically possible with a conventional computer. That could take a while to get to quantum computers that are able to do that. The technology is still not that advanced. But in the nearer term, there's heuristic algorithms, and they don't have the same performance guarantees. Instead, the performance is more uncertain. It can be tested out, and there may be advantages there. We have to test it out to find out.
And you mean heuristic algorithms for
heuristic algorithms? That's
okay.
For example. Yes, exactly. And finally, there's a lot of uncertainty in when the technology will come to, realize real computational advantages. This is related to your nice plot of the advancement of the technologies, right? You can draw a straight line, but there's huge error bars on it that you can put, and it could be anywhere from 2050 to 2035 when we're running fault-tolerant algorithms or something on these scales. So if you get started now, you can be on the cutting edge of the developments as they happen, and they are happening fast.
Franz, let me turn to you.
Okay. I
why
would
should they
say,
care? Why should DOT care? What are near-term applications?
first, a little comment to Shaw's algorithm. So it's actually a great algorithm, and it was mentioned here it would require only a small quantum volume. But in reality, it actually needs the largest one. The reason behind is the following: Grover's algorithm and many of the only polynomially scaling algorithms are based on comparatively simple gates that can be done on a quantum computer, also on an advanced quantum computer. Whereas Grover's algorithm depends actually on quantum Fourier transform and phase estimation, which requires that you can do very, very small rotations on a qubit with very high precision. And that is the question, a general technological question, to what extent this can be done. All the error correction algorithms that are around only allow actually to do corrections for comparatively simple gates. Yeah. So Yaakov was talking about, let's say, 45, 90, 180 degrees rotations. I am talking about microradians of rotations. So that's my little comment to the difficulties.
So that's perfect. So let me just give you a chance to expand on that, Franz, for a second. So Franz, and just to try to get what you said in a sentence. So not all gates are created equally. Some gates are harder than others. Yeah. And therefore, even though someone might say, oh, this costs only 1 million gates, exactly what those gates are actually matter.
Right. So therefore, I would prefer actually in the future not to use quantum volumes or qubits by themselves, but use really benchmarking algorithms to compare quantum computers. Because then you can see actually that some of the algorithms can be done with computers that have lots of qubits. Other algorithms can only be done with small number of qubits. And if you do a Fourier transform with a small number of qubits, that means low precision. You can do that like for a classical computer with a very simple algorithm. Yeah, if you want to have with a classical computer high resolution, you need fast Fourier transform based on multiple computers. So we have very similar problems actually in quantum areas and classical areas in this sense. Where a quantum computer
so why should DOT care?
Right, yeah. Why should they care? Quantum computers can give you the possibility, in my opinion, in two directions. One is there are specific problems or type of problems that can be done by using entanglement or superposition in a much better way than you can do with a classical computer. And the other one that we learned also very much from D-Wave, what you have to do is actually digital twins. Yeah, if you really want to use a quantum computer, you first have to understand, you model your problem very well, because then you can separate out parts of the graph and calculate that on a quantum computer, do maybe other pieces on a classical computer. So these two directions.
And in terms of near term, any thoughts?
Near terms, for sure, any optimization problem. And I think later on we get into sensing, where there are actually also applications where sensing can be combined with quantum computers, which is actually a very interesting topic. Unfortunately, very nascent right now, but I believe that within the next 5 years, we get that actually.
Quantum sensors we're going to push off for a little bit. Okay, great. But Thomas, I'm going to go to you. IBM has identified use cases. IBM has certainly, as you've mentioned, you had a list up there. What are some of the ones that you want to emphasize to our audience here, and how long do you think it's going to take? What are near-term applications?
So you can find this online. It's called the quantum decade. So we're in the quantum decade. Think of 2020s as in the quantum decade. So during this decade, we've come from a tremendous evolution of just starting quantum computing. And as we exit this decade, we'll be closer to that fault-tolerant quantum computing capability that was cited earlier. Not quite as far off as 2050 and beyond. It's nearer in, especially with the error correction capabilities that are there. The nearer term quantum capabilities that are here, there are multiple waves. Quantum machine learning capabilities and some of the simpler quantum optimization problems can be solved with today's what we call quantum utility, or the early, noisy, intermediate, scalable quantum computers. You can start to solve those problems, and that's the time frame we're in now. And by the end of the decade, we handle the more complicated ones.
All right, I'm going to give a non-quantum answer. You all are in the public sector. You are there to provide public sector benefits, whether it is through FAA, pipelines. You have to provide information for infrastructure. You need to do it better than you did it yesterday. It may not be perfect, but you need to do it better. And that's where quantum computing, especially today's quantum computing, can help. There was a company that was talking in Boston about cargo loading, and they were able to, Unisys, they were able to provide a solution in 7 seconds that would have taken them classically 7 years to solve. In Japan, they have built tsunami evacuation routes utilizing quantum computing applications. So is it the ultimate, and I'll go back and forth with Yaakov about the word universal, but a fault-tolerant system, because I don't think any quantum computer will solve all problems all the time. There will be different capabilities for different ones, but what can we do now that's better? And the use cases I had listed earlier are, as Franz mentioned, the optimization ones. How do we get FAA working better? How do we get infrastructure working better? How do we do EV charging station placements better? How do we manage our electrical grid? How do we manage the pipeline side of things? Those are all optimization problems. They're low-hanging fruit. Eventually, we'll get a system that's big enough that can do material design and design a new car that's lighter and doesn't need as much gas or electricity and things. That's in the future. That's for our companies to worry about getting systems that big. But from your perspective, what problems do you have right now? And if you could provide a solution that provides benefit, uses less computational power that an energy consumption that a classical computer would, that you could do with a quantum hybrid solver, that's why we're here today.
Okay, so I'm going to turn the question around and go backwards now, because Allison, are you claiming that DOT can solve some of their problems better now using a quantum computer than they could on a classical computer?
Yes.
Okay, and is that for a lot of problems, for some problems?
For some problems, optimization problems, and I would say the phased approach that D-Wave takes is actually use case identification as the first phase, because not all problems need quantum, not all problems can be solved with today's quantum. The question I had earlier about benchmarking, and I know we've talked about it before, is not all systems act equally. So there are some that, you might want to try a multitude of different quantum things, but Unisys is using stuff today. There was a company, Savant X, who I believe is online, that built an application that the Port of Los Angeles used in real time, optimizing one cargo pier. So in real time, so as trucks were coming, so changing the cargo optimization of those routing. So yes, it can be solved today. Not every problem can be solved.
Thomas, you mentioned quantum machine learning. Is that something that you're ready to put forward as a, yes, you should be using this today, or this is something that still needs to be worked on?
So quantum machine learning can be done today. I've worked on problems in flash flood forecasting and actually solved them more accurately using quantum machine learning with a select data set than using classical machine learning. Now, it's not trivial. It takes a while to figure out and determine how to do that effectively, and it's very data set dependent. At this point in time, you can think of quantum machine learning, for those of you who are data scientists or information scientists and have familiarity with that. Think of it like another set of algorithms. So just like there are different variations of machine learning and neural networks and deep learning, quantum machine learning is another variant of that and will continue to grow in its capability. Today, it's able to do problems similar to, I'd say, fundamental types of machine learning at this stage, but it will grow in its ability to handle data, and handling data in partnership with classical computers is necessary in order to perform. So it's not going to ever do it independently. It will only be in collaboration with classical computers, managing that data, but all the processing can occur, and there are algorithms and data sets that are better solved using quantum computing than classical computing today.
Franz, what do you think? You buy it?
I buy that. Yeah, so the combination of quantum computing and classical computing, that's a critical point. Yeah, so what we call QPU as an extension or an addition to GPUs, yeah, that we have quantum processor units and not only graphical processor units or interfaces, yeah, DPUs or so. So that is actually what I see the future for quantum computers as an additional computational possibility in order to speed up specific parts of classical problems. Yeah, in many problems you have, let's say, you are dealing with lots of data, let's say CFD, where you have large grids. That cannot be done simply directly put on a quantum computer, but specific calculations take very long time on a classical computer, can be done very fast in a quantum computer. So I could come up with a long list of that, but simply say that in general form.
So Phil, you mentioned that through Oak Ridge, people, including people here, can get access to some of these systems that both Allison and Thomas are talking about. So are there tools for them to actually test what Allison and Thomas are saying?
So
I'm not trying to speak badly about them.
Yes, yes.
We want proof.
We currently offer access to IBM computers, which Thomas is associated with. I do not believe that we currently have access to D-Wave through the Quantum Computing User Program. Yeah, I guess you said we're working on that. We've partnered with D-Wave in the past.
In the past.
Yes, definitely. Yeah. Okay, so that said, there's also documentation online to learn about these algorithms and try to find ways to fit them in with your use cases and things we'll identify later today. That said, I want to also maybe push back a little on some of the comments from the previous distinguished speakers, and they can correct me if I'm wrong, or they think I'm wrong. In my understanding, most quantum computational demonstrations today are more like proof of principles than actual application scales. If you want to run a large scale optimization problem on a digital gate-based quantum computer, that is probably not possible. Now, I want to also clarify that D-Wave and the stuff Allison was talking about is different than these digital gate-based quantum computers. The D-Wave computers run a specific annealing algorithm, which is more of a special case, and it's designed most naturally for optimization, and they can handle very large problems. And if you want to handle large problems, that's probably the best place to look for that. On the other hand, IBM computers, the ion-trapped ones, Quantinuum, and so on, have something like 100 quantum bits or fewer. So you can only solve a 100 variable problem or fewer variables than that. And if you want to do a large-scale problem, it's not going to be straightforward to do that with these computers.
So
do the other speakers think this is a fair comment?
Yeah, I'll comment. So yeah, I agree with everything that you said in terms of the number of variables that can be handled today. And bear in mind that 2 or 3 years ago, that variable count was 5, 10, right? So over the course of a few years, it's gone from 5 or 10 up to 100. Over the course of the next few years, it's going to go from 100 to 1,000 to tens of thousands in the relatively near and foreseeable future. So that's the capability. And absolutely, the number of data points that can be handled is limited. Today, it's in the thousands, maybe up to 10,000. So it's limited today, but it's going to grow significantly in the coming years. So where we are today, absolutely, and where we're heading is going to move very quickly.
Yeah. Did you want to comment?
No, I agree. But I also think that when you look at the quantum processing unit, as Franz mentioned, that limitation versus if you do a hybrid solver, you can actually potentially look at even bigger ones. So D-Wave just released a new hybrid solver that's looking at nonlinear problems, and it actually goes up to 2 million variables. But again, it's a different type of system, and it's, as was mentioned previously, annealers are looking for and best suited for optimization.
So Phil, I think you effectively just answered this question by your previous comment, but besides just access to the systems themselves, why should DOT pay attention to Oak Ridge?
Why should you pay attention to Oak Ridge? Apart from the providing access to the computers, We're trying to, the point of the labs is to advance national interests, and obviously advancing the DOT goals is part of advancing those national interests. So we could be partners for you with that. We also have the world's fastest supercomputer, which is a test bed for comparing against any algorithmic approach that a quantum computer may advance. And assessing whether this is really beating the best classical solution.
You should all go see that computer because it's really now let's go to the quantum computer quick. Franz, you come from an interesting organization, right? Academia plus merged with industry. Why should COT pay attention?
Okay, I think I said that already. There are some parts that can be done in a much better way or more efficient way on a quantum computer. Other parts is also developing. Maybe I should mention that as well. So in parallel to quantum computing, classical computing actually also started to develop new algorithms, improve new algorithms. Yeah, let's say all the supremacy statements here, they were actually all overtaken by classical computers. So last month, for instance, a Chinese group actually did the same thing that Google did a few years ago on their computer and were claiming it takes more than 100,000 years to do that on a classical computer, could do it faster than the quantum computer, needed less energy than the quantum computer. Yeah, simply there's a development which can be accelerated very much in both directions, classical algorithms as well as quantum algorithms.
So Franz, let me actually change the question for you slightly, because both Mukund and especially Gretchen mentioned the importance of the quantum workforce. So you are on campus of University of Maryland. How is QLabs, right? How is QLabs? How is University of Maryland? How is IonQ? How are they helping solve this quantum workforce problem?
I think, okay, I have to admit personally, it's almost insolvable.
Okay.
Actually, Gretchen is one of our faculty. She is working in the Joint Quantum Institute at UMD, and she mentioned already right now we have the difficulty that we can't keep any postdoc. Yeah, so all the postdocs that are working for us on ion traps are later on at IonQ or Continuum, who are working on natural atoms are QAra, QNECT, and other companies. And for the superconducting, we have several people also at IBM. So that is actually a big challenge for academics, yeah, to get research moving on into the future and not start everywhere from scratch. What we are trying to do is actually developing new programs inside the university. We are offering right now also a master in quantum technologies, which is it's an interdisciplinary approach, which are using approaches from engineering, physics, computer science to bring everything together.
Yeah. How much time do you have left? 10 minutes. Okay, we want to get to audience questions. Okay, so Thomas, Allison, I assume that it is given as to why DOT should pay attention to your organization.
Well, I was actually going to go into the workforce side of it, which is as you're developing these algorithms, identifying use cases, your own internal folks will learn what can be done, how it can be done, where it navigates. And so you're actually, as you're coming together, it's not like you're handing a problem over to a company, they go solve it and hand you back a solution. You're actually coming together and building it together. So you're actually doing a workforce development internally and building that internal need, which is so desperately.
Okay, so before we get to questions, 30 seconds, favorite use case, Thomas, go.
Favorite use case is what's available today, quantum machine learning for natural disaster forecasting and improvement. We're working on hurricane rapid intensification with an insurance industry company today, and it couldn't be more timely than what just happened last week.
Awesome. Franz, 30 seconds.
Yeah, variational quantum algorithms, in particular, finding out ground states and excited states of atoms and molecules for material development.
Cool. Allison.
Mine is anything that shows a real ROI. If I can get a solution faster and do something better, it's my favorite one. And there's a lot in the transportation.
Because I like you, Allison. We're going to let you get away with that one. Let's go. Maybe use case.
Optimization algorithms and quantum simulation of
Awesome. All right, audience questions. How do you want to do this project? Anybody? Any questions in our live audience? Please.
I have to do costing of new technologies, new platforms, and so forth, proposed airplanes, so forth.
Yes.
One of the methods, of course, is risk analysis, risk evaluation. To get there, you got to do, say, a Markov chain Monte Carlo simulation. Is that an annealing problem, simulated annealing, or quantum annealing problem, or is it applicable to another type of quantum architecture?
Good. Bill, you're our algorithm guy. What do you think?
Markov chain Monte Carlo, quantum linear algebra might be helpful there. I'm not an expert on, that specific algorithm or the quantum approaches that have been helped for it, but that's what I would think of as a way to get started.
It's a form of optimization.
Yeah. Allison, Tom?
And as I started, I'm not the technical person. I'll connect you with Jameson, who's in the room, and he will get you that answer directly.
Financial industry companies are doing that today. We're working with them at this point in time. They're not of a large scale at this point in time. You won't be surprised by that. But yes, there's early work that's going on that front. It's a little bit longer term, not quite as near term.
Franz?
Okay, it was already said.
Okay. Question.
Craig Thor, Federal Highway Administration. So I know from talking to Dan and Prachi that part of the point of this workshop is to kind of get ahead of the game on quantum, something that we missed the boat a little bit on AI. We did a lot of AI research early, but some of the new stuff is really, we're not quite there for it. We have some of the same workforce issues that we've already talked about on AI and data science and recruiting to work with the federal government. So what can we be doing on the federal side to make sure that we're prepared for these technologies that are either here today or coming down the road? Whether it's in 10 years or 20 years, whatever it is, but making sure that we're preparing to be ready to accept these technologies and put them into our research portfolios and things like that.
Right. Who wants to address that question?
I can answer something that happened in Tennessee. I don't know if this is something that can be scaled across, but I know the Wondery, which is part of Vanderbilt, actually pulled together different universities with Oak Ridge, worked with D-Wave, IBM, Zapata AI, which is a software company, to do workforce development and identifying what are the problems within the community of Tennessee, and then trying to help train the staff up. So it was actually doing use case identification and workforce to try to solve a problem that was real. And I know that there's a lot of NSF funding programs that also kind of help support that. But for me, it's kind of getting those communities, identifying the problems. We in the companies, we think we know your problems, but we actually don't. And so that's why the workshop later today will be so great, to better understand what you guys are facing and then work with the local academia trying to build solutions for you.
Anyone else? So let me also just quickly comment. I'm trying to stay out of it so our panelists can talk. But University of Rhode Island just started a program called Quantum Pivot, in which is appropriate for people mid-career who want to learn about quantum, be able to pivot towards quantum technologies. So that is an online course, which actually MITRE is part of, but that's, I'm leaving that out for the moment. But, other questions, please.
I didn't hear it. Can you repeat the
Oh, sorry. Yes, University of Rhode Island has a program called Quantum Pivot for people already mid-career who'd like to be able to, play a role in quantum technologies. Yeah. Is that right? Is that our thing? Oh, because I think here. We've got major DOT stuff going on right in the hallway. The traffic jam right out there.
We could have optimized it.
What are you going to do?
questions online.
Yeah.
First, so we have Danielle who asks, how do you verify and validate quantum computer solutions? Classic computers take way too long to solve the same problem. How do you validate?
All right, IBM, that's on you.
Yeah, so it's a great point. Certainly those that are of the scale that can be simulated from a classical computing standpoint is one validation point. So I'd say for the near-end capability, often, although it's a longer duration, there does exist the classical computing simulation abilities for many of those problems. And when that new groundbreaking technology is arrived at, there was a problem on the cover of Nature magazine June of last year, and another one in May of this year. So look those up on the cover of Nature magazine. And essentially, when we exceed the classical capabilities, it's going to be very challenging to validate those solutions. I'm not sure. Franz probably has a better view.
I have a very different view for that. For most cases, you can actually do a simulation, at least for part of the problem. The other part is, as I mentioned, new development also in the classical computing. So if you look into tensor networking, that allowed actually to do the same thing that Google claimed takes millions of years on a classical computer, actually was faster than a quantum computer. Similar actually to last year's publication in Nature from IBM. Shortly afterwards, actually, a group figured out you can do that even on a very old Commodore 16-bit computer, and get faster solution out than on the quantum computer. What is behind is actually that we have to learn to get away from simple linear algebra and move into new developed tensor networks or sparse matrix algorithms. So these specific problems, they were comparatively nice to optimize on an IBM machine, and the group did a very great study on using error correction algorithms. But as I said, classical computers often can do it even better. We only have to learn how to do it. And in my opinion, we only can learn it when we work together, quantum and classical part.
Yeah, really, just to emphasize what Franz said, a really excellent question from Danielle. But conventional computers are not staying still. Conventional computer scientists are being spurred on by quantum computing to show that no, what they're doing can be just as good. And so that's what Franz is. Franz is really helping us to understand that.
I have one more, and then I'll hand it off to Dan for any more questions. Danielle, she also asked, actually, this is based on Franz's point earlier as well. You mentioned, quantum computing requires problems that are very well defined, but also very large. So does this mean we should use it for deterministic rather than probabilistic problems? Does that benefit of running this?
Actually, never uses for deterministic problems, because therefore you don't need actually the large probability space. You need that for probability problems. So quantum machine learning itself has a really big problems on classical computers because they are digital. Quantum computers on neuromorphic computers would give a much better chance to do these things. We only haven't learned how to do it.
So do you want to comment on that?
Yeah, so I think that for existing technologies, the probabilistic problems are a lot more natural, but future known algorithms do have deterministic answers, like Shor's algorithm for factoring, and the quantum computer still helps on that. So in the near future, probabilistic problems are probably natural, but in the farther future, deterministic problems will also be very natural, and they actually have known speed ups for these problems.
So my question, let me unfold it a little bit. So I'm old enough to remember assembly language. We had the conversation 50 years ago, similar to what we have today, about how many chips we can fit in a silicon wafer. And we had people who were thinking in the software part of how to move these bits around. Today, I sense a little bit of that conversation. We're talking about hardware, how qubits I can put it, how can I make them, how can I keep them in place. And I sense that somewhere in there, there's the software. Somewhere there's the equivalent of the assembly language that the fundamental programmers are going to use to develop tools the rest of us don't really care about anymore. Nobody really uses assembly language. We're using interpreters and compilers that are built that gives us languages like C++, Python, whatever, that allows us to use this trillions of transistors inside. We don't think that on that level anymore. So in terms of investment for the DOT, is it an investment in hardware development, or is it better an investment in creating the software languages and the software tools that are going to say, you want to do this function? Well, put it in this subroutine that will use the QPU and do it faster than the GPU.
I'm happy to start there. So I think that's an amazing question. I'm glad that you brought that up. Almost all quantum computers are available cloud now. So it's not about purchasing hardware from a DOT perspective. It's about accessing the cloud and working with the different companies to identify how do you write your code for each of those. From a D-Wave perspective, it's Python. We have a training program, and we can talk about that later. But there's a way in which to identify those algorithms. I also believe that different systems are going to have different capabilities. And just as you said, you don't care about the hardware chips anymore. But what's going to end up happening, I assume, in 5-10 years, is you're going to have an integrated data center. You're going to submit a problem online. It's going to take that problem and break it out and send it to whichever QPU is best to solve it, whoever's qubit architecture there. It will also send it to a GPU, and then you will get the answer back. So in the future, it's going to be kind of this cloud access hybrid, and there will be an algorithm that breaks down your problem.
Great. Thomas, yeah, IBM has certainly been thinking about this.
So there's a software development kit called Qiskit, Qiskit. 70% of the developers on quantum hardware use that common software development kit called Qiskit. There are over 600,000 global users of that application that exist, and it's a building block, and there will be more and more functionality added to it. It's all about the software and scaling the software to make the functions of the hardware seamless from the end user's perspective.
Little comment to that. Please. Sorry that I have to say that. What's missing right now is actually good transpilers. That means Qiskit is a nice language. Okay, I'm using that as well, but use also others. The important piece is actually how this software is then transported, let's say compiled for quantum computers. And that is not at all optimized. Doesn't matter which language you are looking at, they are really poor quality stuff. Yeah, you can do much better optimization simply by using specific rules, quantum mechanical rules, etc. And that has to be built in. So what I hope that happens in the next 5 to 10 years, that we get actually to the point that we have good compilers for quantum computers. That is a crucial part.
Yeah, and let me just throw in that there are a number of companies that are trying to address exactly this type of question.
Right.
Q-Control, for example, is trying to do exactly what you said, Franz, trying to optimize the language and trying to make a compiler that will work. How are we doing on time?
Yeah, I think we have time. If you have more questions, the panelists, they're going to be here throughout the day, so we'll have lots of time to ask any questions. Really quickly, we'll take a 5-minute break. If you go around the corner on the right and take another right, there's food, there's water, and some muffins. If you take a left, there are bathrooms. We'll come back in 5 minutes, and we'll get to something that's more near-term, quantum sensing. So see you all shortly. Thank you.
So I'm actually happy that you developed.
Okay, great. So we can define quantum sensors as devices that leverage quantum phenomena to measure physical quantities. Those physical quantities include things like acceleration, for example, or say the amplitude of a magnetic field. And the reason that people are interested in developing quantum versions of various sensors is that they can offer improved performance in some metric, maybe sensitivity or stability, for example, or they might offer the potential for smaller swap, smaller size, weight, and power compared to traditional classical sensors. So there are a number of different types of quantum sensors. There are quantum versions of clocks, inertial sensors, gravimeters, which are sensors that are engineered to measure the acceleration due to gravity. You can think of them essentially as mass estimators, magnetometers, electric field sensors, and photonic devices that are either leveraging or detecting quantum states of light. At the bottom here, I've listed some potential applications for these sensors. A number of them have the potential to contribute to complementary PNT techniques, that is, positioning, navigation, and timing techniques that are complementary or alternative to GPS. So these include things like time holdover, so maintaining precision timing in the absence of external timing signals like GPS, inertial navigation, gravitational anomaly-aided navigation, or GravNav for short, and magnetic anomaly-aided navigation, or MagNav for short, are position fixing techniques that rely on map matching to pre-existing gravitational or magnetic maps to figure out where you are. And then also applications like radio navigation and geolocation. So a number of the electromagnetic and photonic sensors may also have applications in resilient communications, And then there are other applications as well for some of these sensors, including things like subsurface mapping or near-field metrology techniques, and even potentially down the road, things like chemical and biological sensing as well. So there's a wide range of technology readiness of these quantum sensing devices today. The scale I'm showing you here ranges from laboratory demonstrations up through commercially available systems. And everywhere that you see a red dashed line around one of these bubbles, that means that there's at least one prototype version of that type of sensor that has undergone a test or a demo in a relevant environment or a use case of that sensor. And I'll tell you, just a few years ago, there would have been far fewer red dashed lines on this chart. We are really in an exciting time in this field right now, where a lot of these technologies are starting to get out of the lab and into relevant environments for testing and optimization. So today, with the limited time, I'm just going to focus on 4 types of quantum sensors, namely clocks, inertial sensors, gravimeters, and magnetometers. But I'm happy to discuss any of these sensing technologies with anyone who's interested in more information at a later time. So I'll start off here with atomic clocks. So atomic clocks are really the oldest and most well-established quantum technology to date. They've been around for 75 years. The commercially available atomic clocks today range from these small-sized chip-scale atomic clocks up through these very high-performance and large hydrogen masers. These technologies really underpin many aspects of our life today. We use them in GPS, we use them for telecommunications, we use them for timestamping of financial transactions. And many of these technologies have approximately in the very simplified architecture I show in the upper right here, they basically have, I think it was mentioned earlier that 99% of every quantum sensor is comprised of classical technologies, and that's true for all of these as well. And most explicitly, in all of these clocks, there's actually also a classical clock. And how they actually operate is using sort of the intrinsic stability of the atoms that are in what we call that physics package to stabilize the frequency of a classical oscillator. And that gives us the RF output. And so the goal of the atomic clock here is really to create that RF output, a nice stable frequency that is more stable than it would have been had there not been atoms that are helping to stabilize the frequency of that classical local oscillator. So the vast majority of atomic clocks today are what we call microwave atomic clocks because they rely on driving microwave frequency transitions in atoms. Over the last 25 years, there have been developments in another class of atomic clock known as an optical atomic clock because they rely on driving optical frequency transitions in atoms. And the reason that people are interested in developing these is that it turns out that the stability of an atomic clock is actually directly correlated with the magnitude of the frequency of the electromagnetic field that you're using to drive those transitions in atoms. And so by moving from these microwave frequencies to these much higher optical frequencies, we actually expect intrinsically better performance. And so some of these big, laboratory scale systems that are spread out across optical tables, they've really been showing that to us. In recent years, they've been setting records in terms of stability, in terms of uncertainty. They are extremely exquisite devices. And they're so good that about 2 years from now, they are going to start contributing to international atomic time. Metrology institutes around the world that have these optical clocks are going to start contributing to international atomic time using these new devices. In addition, just this year, in 2024, we are starting to see the emergence of commercially available optical clocks as well. So here I'm showing you a picture of a rubidium version that I'm sure Max will tell you more about during the panel, and then also an iodine version from Vector Atomic. There's a version of this iodine prototype that was recently tested for multiple weeks in a maritime environment and actually demonstrated comparable performance to some of these commercially available hydrogen masers, but as you can see at a much smaller form factor. So how do all these clocks measure up relative to one another? I'm showing you one metric here, which is called the fractional frequency instability. This is a metric that describes the short-term stability of atomic clocks and as a function of the volume of the clock. This chart is actually one that we were able to generate thanks to QEDC, who you'll hear a bit from later. So there are two main things I want to point out on this chart. So one, as I mentioned, is that these emerging optical clocks are really starting to offer comparable performance to these extremely exquisite, existing commercially available hydrogen masers, but with a much smaller size. The other is that, as it was also mentioned for quantum computing technologies, even though we're seeing all these nice advances in the quantum versions of these systems, there are also parallel advances happening in classical technologies. And so there's actually these emerging classical MEMS oscillators that are starting to compete in terms of short-term stability with some of these chip-scale atomic clocks that comprise kind of the low size end of that blue bubble. So as we move forward, I think atomic clocks are still going to be the best solution for any situation in which you need something with really good long-term stability. But if you only need something with very good short-term stability, say a few seconds of holdover from GPS, then you should also be tracking some of these advancing classical technologies as well. Next, I'll move into inertial sensors here. So there are two primary types of quantum inertial sensors. There's one based on a technology called atom interferometers. There is another based on a technology called a nuclear magnetic resonance, or NMR, effect in atomic vapors. And I'll note the top one here is actually something that's been very recently developed. This is actually a space-qualified gyroscope that's expected to launch relatively soon with support from the Defense Innovation Unit and DoD. And a lot of these systems, so depending on the development of the test environment, how you're going to use it, I also want to point out that these inertial sensors, as well as the gravimeters that I'll show on the next slide, if you're putting these systems on a mobile platform, which I assume you're doing if you're using an inertial sensor, you will actually obtain likely maximal benefit and best performance if you combine this quantum hardware with some classical inertial hardware. A lot of these systems, for example, the atom interferometers, are very well suited to help correct for long-term drift, but they are not so good at picking up extremely fast inertial movements or vibrations of the platform that would otherwise cause errors in your overall inertial navigation system. So you actually can get a lot of benefits by, say, in this upper right here, combining your quantum hardware with your classical inertial hardware to get the best possible measurement and estimation of the inertial motion of your platform. So where do these systems measure up with respect to classical devices? So I'm showing here one metric that we use to describe inertial sensors, which is the in-run bias stability as a function of the volume of these inertial sensors, specifically for gyroscopes. And so you can see here that, for example, the NMR gyroscope provides good performance with a better performance than some of these MEMS gyroscopes, but with a comparable form factor. These atom interferometer systems are really just starting to come out of the laboratory and starting to undergo miniaturization. But there are some upcoming programs that are really aiming to take this performance that they're exhibiting in the laboratory and putting them into a smaller package so that they have a more comparable form factor to some of these fiber optic gyroscopes. So the main takeaway, the main value proposition of these systems is that they offer the potential for high performance with a comparable or smaller form factor than traditional classical inertial sensors. Moving on to gravimeters here. So there are two primary types of quantum gravimeters. There are those based on that atom interferometer technology again, as well as those based on superconducting systems. Both of these are commercially available devices. And the main advantage of these systems compared to classical gravimeters is actually that they offer much better long-term stability and accuracy. I've heard it said before that these atom interferometer systems are essentially, they're like the turnkey device. They can be engineered to be nearly self-calibrating so that you do not need to recalibrate them every time you move them to a new location. Some recent developments in this technology include demonstrations, for example, in the UK, mapping out the location of an underground tunnel, monitoring volcanic activity on Mount Etna, and then also a recent maritime demonstration as well, mapping out gravitational anomalies on the ocean floor from a surface ship. So some applications of this include, as I mentioned earlier, GravNav. That was one of the motivations behind this gravitational map demonstration. subsurface mapping, like was done in the UK, and then also mineral exploration as another potential application. And then finally, I'll give a quick overview here of quantum magnetometers as well. So there are 3 primary types of quantum magnetometers. There are superconducting or squid magnetometers, those based on atomic vapor, and then a third that is based on defects in solid state crystals, one of the most common being, nitrogen vacancy centers in diamond. So all of these have different sort of advantages and disadvantages, trade-offs in terms of size and sensitivity and dynamic range, and they all have application spaces for which that they are well suited. So squid magnetometers, for example, are already in use for things like biomagnetics, monitoring and imaging, brain and heart effects, and then RF comms and sensing as well. And then some of these, much smaller swap systems based on the atomic vapor or the solid state defects have been under development for magnetic anomaly detection, including applications for MagNav as well. In recent years, we've seen a much wider commercial availability of atomic vapor-based magnetometers, including, I think, at least 4 domestic companies at the moment. And then we've also started to see a lot more testing and development of both atomic and solid-state based systems for MagNav applications as well. And I do want to point out that for this application in MagNav, there are both classical and quantum versions of these sensors that are sensitive enough for MagNav. You really only need a sensitivity of roughly a nanotesla to be able to do MagNav. But if you want to do MagNav, if you want to generate highly accurate magnetic maps and then do active magnetic navigation, you really ought to use a quantum magnetometer. And the reason is not for sensitivity. The reason, again, is for that long-term stability and accuracy metric. That is what's going to give you the highest accuracies and the best reliability for magnetic navigation. So I'll conclude here just by kind of giving at least my perspective on the outlook for some of these devices for DOT. So some of the nearer term applications of these sensors include complementary PNT techniques and things like subsurface mapping. And the main things that I hope you will all take away here is that I think the key advantage of these quantum sensors for these applications is really in their long-term stability and accuracy. I think there's a common misconception that, oh, quantum sensors, they'll give you better sensitivity, so that'll make everything better. But in a practical environment, what the primary benefit that you're actually getting is in their long-term stability and accuracy most often. The others that, so those position fixing techniques I called out, MagNav and GravNav, they are not going to be suitable for every platform. MagNav is being developed primarily for airborne platforms, GravNav for maritime platforms, and even for those platforms, they may not be the best option for positioning for you. But if they are the right choice, they do have certain advantages in that they're completely passive. They don't require you sending signals out into the environment. They can operate any time of day, all weather conditions, unlike some vision-based techniques. So if those are the right techniques for you, you will most likely want to use a quantum sensor to help support map making and active navigation, due again to their good long-term stability and accuracy. And then looking farther out, what could these do? So, I sort of limited the scope of the talk today to some of these nearer term devices, but a lot of these systems are still in nascent development stages in laboratories. So we can think about other potential applications, for example, quantum-enabled optical devices for chemical sensing of hazardous materials. We could think about using nitrogen vacancy centers in diamond, not for magnetic sensing, but instead for strain sensing, which is one proposed physical quantity that they can measure. And perhaps as those devices continue to get smaller and more practical, they could offer early identification of structural integrity problems for bridges or other critical infrastructure. So with that, I think we can move into the session with our panel. Okay, so I think we can welcome up Mike Slocum from AFRL, Rishu Wright from NETL, and Max Perez from Inflection. And I hope all of your microphones are on. Okay, so I think everyone's going to give, I think, kind of a quick overview of themselves and their organizations to kick us off here. So I guess we're starting with Mike, it looks like.
Yeah, go to the next slide.
Yep.
So yeah, Mike Slocum, AFRL, Materials and Manufacturing Directorate. So in representing AFRL, we have, thank you. Numerous different efforts across quantum that we work in multiple different research directorates. So, you know, efforts in optical atomic clocks, magnetic navigation, which is where I primarily work in, but also in quantum communication and computing as well, where, you know, high brightness optical sources that can be used for space or Earth to space links, as well as looking at increased coherence time on superconducting qubits. So if you go to the next slide, we care a lot in the Air Force about PNT and you know, particularly in navigation in the absence of GPS. So have numerous different efforts spanning all the different complementary navigation sources. And the reason why we need complementary navigation is because we can't depend on any one solution in the absence of GPS. And sort of, I'm not going to talk to any of the details on this chart, but you know, there's always going to be trade-offs no matter what you're doing when you get rid of GPS. If you're over ocean, you can't depend on vision. If you don't have a map for magnetic navigation, you can't depend on it. And there's a key difference between some of these. So inertial, there's always a drift related to it. So when you have something that has a drift component to it, we need to have something that has an absolute reference, like a map-based technique, like magnetic navigation or GravNav. So we absolutely need a portfolio of different solutions, some classical, some quantum, you know, to be able to provide resilient navigation in the absence of GPS. And that's something that we're working on across AFRL. And then if you hit the next slide, my approach, at least in terms of what we're working on in navigation or in quantum systems, is to really take a systems engineering mindset as we're approaching some of these different challenges. So this is sort of a snapshot look at the development of just a nitrogen vacancy-based sensor, where we're trying to understand the sensor requirements in context of the application and how that feeds into the subsystem and system requirements and how that all comes together as a holistic system and how we develop all of the different components to build that overall system. So it's not just working on the exquisite physics, it's actually taking an engineering approach, and how do we take that engineering approach to ultimately develop the solution. And like Mukund said earlier, you know, 99.5% of this is all classical. You know, it's really taking a engineering classical understanding, how do we develop these quantum systems to get this solution that we need, and that's what we're trying to do.
Okay, thank you, Mike. And Rishu, move on.
Thank you. Good morning, everyone. My name is Rishu Wright. I'm a research scientist at DOE National Energy Technology Lab. I also serve as the technical portfolio lead for our method mitigation portfolio. Next slide, please. So NETL has been working on the infrastructure sensing and for almost actually more than a decade now. And one of our large portfolio is pipeline monitoring. So I think that's a really good intersection between like DOE and the DOT interest. So and for the pipeline monitoring, we have a strong expertise in distributed optical fiber sensing and passive wireless sensing. So the two key, by the way, is my mic on? Everyone hear me well? Okay, perfect, thank you. So there are two key parameters that we try to monitor for pipeline monitoring. One is the structural integrity, and we try to identify the corrosion as a predictive signatures that try to detect that early so we can prevent any failures of the pipeline. And second one is the direct signatures. When the pipeline fails, then the gas will emit or leak from the pipeline. So how do we achieve that is we use those two sensing platforms and also functionalize the devices to achieve those two key parameters. And as you can see, the classical sensors provide a lot of good advantage to it already. You know, the interrogation system of distributed optical fiber sensor can achieve more than 1,000 kilometer interrogation distance and also less than 1 to 5 meter spatial resolution. Then how does the quantum technology come into the picture? So next slide, please. So some examples that just to show how we can consider in this quantum area. One is the quantum enhanced fiber optical fiber sensors. So classical sensors are very good already, but it's still limited by physics by the system noise, particularly the short noise. So the quantum enhanced sensitivity and resolution will be better. And so some of the, as you can see in the picture, so you can imagine one of the quantum enhanced system, the interrogation system can be enhanced with a single photon detector, and also that will provide more sensitivity. So some potential application area would include like pipelines, storage tank monitoring, and wellbore monitoring. And one of the tables shows the example that how the sensitivity might be improved using the quantum enhanced fiber optic sensors. So we just picked the temperature as one example. So you can see the temperature resolution is increased by 1 order of magnitude. So this is still one area that can be explored for pipeline monitoring. So next slide, please. And come to the gas leak detection. So there are actually relatively more mature technology that's available. One is the quantum LiDAR that you can detect. I think it was mentioned by some previous speakers as well. So it can identify the gas leaks with more accurate and more higher resolution. And another technology, also quantum related, is by LongPath. I think they just got awarded by a large fund from DOE. So this is to quantify methane emissions over large area using the quantum enhanced spectrometer to provide more accuracy and quicker measurements. Next slide, please. So this is a summary of NETL's quantum technology capabilities. So today the topic is covering quantum sensing, but at NETL we also have a team working on quantum computing as well. So and also I'd like to acknowledge the colleagues within the quantum sensing team as well. So that's all. Thank you.
Thank you. And I'll hand it over to Max.
Hi, everyone. I'm Max Perez. I'm the Vice President of Strategic Initiatives at Inflection. Our goal at Inflection is to bring together resources from across the nation, across the world, make those quantum resources available to our partners at the U.S. government and particularly the DOT and other organizations that are interested in quantum. That could be photonic or laser, compact lasers from the Santa Barbara area. It could be the cells and hardware products that we make in Boulder, Colorado, quantum computing work that we do in Madison, or the quantum software and applications work we do in Chicago. We also have an office in the UK that makes available the resources available overseas, as well as a new office that we've established in Australia. So the ability to bring those together through the private sector and make them available to our partners in the government is one of our main goals. Next slide. Bringing together all those resources allows us to make a number of products. All those products start with our cells, or the houses for the individual quantum elements or the atoms that comprise this technology. I want to thank Bonnie for actually making a very, very clear point. When you think quantum, think stability, and that stability comes from the ability to isolate the individual quantum elements from the environment, except for the specific thing you're trying to measure. That's kind of the fundamental nature of quantum sensors. The other part of quantum sensors is making those technologies small enough that you can actually get them out in the world. And that's really what we do here. Here are a couple of examples. I'll show them through our conversation, but basically this is the technology that does both the isolation and allows those quantum elements to get out into the world. From this base technology, we can make a number of products. The product I'll talk about the most is our ticker optical clock that will essentially enable us to do GPS quality time with holdover on the orders of days to weeks, which is critical for providing assured PNT for our timing infrastructure. Moving forward, Skywire, which will enable passive RF receivers over a very broad spectrum and broad bandwidth, for example, providing a jam-proof GPS receiver. Exact inertial technology that provides that stability over long periods without access to GPS, and Scorpius, which is our quantum computing product. Next slide. One of the main things that we're doing right now, even though we're making our ticker technology available in a near-term form factor, is actually providing the compact elements that will bring this down in both cost and size that make it available across our infrastructure. Make these technologies, and this is not just for clocks, this will be for all manner of quantum sensors, make that technology available at a price point and a size that it can be distributed across our infrastructure to provide that same stability and security for PNT throughout the country and eventually throughout the world.
Okay, excellent. Thank you so much. So I think with that in mind, I actually might want to throw it back at Max here and then come back along the panel because you're all developing technologies with slightly different timelines to deployment. And Max, you just showed that nice timeline on your slide. But of course, there's a difference between when your company is going to have it ready to get it out the door and when it's going to be broadly adaptable into existing systems. Can you speak a little bit as to your perspectives for the outlook of when we'll start to really see a broader scale deployment and adaptation of some of these technologies?
Yeah, absolutely. So the backbone of position navigation and timing is going to be timing. Timing is at the core of all these technologies that I think are of interest to the Department of Transportation in the near term. What you saw on the screen right there is our first generation optical atomic clock. It will be available it's in pre-production now. It'll be available in production next year for commercial and public sector deployment. That said, this is a relatively expensive unit, a couple $100,000. It provides a unique capability that we think people will start pulling in the near term, but at that size and that price point, you don't expect deployability other than in the most critical systems. It's just too expensive, it's too big. And that's where many near-term quantum sensing technologies are today. The quantum magnetometers based on atomics tend to be a little more expensive than might be in everyone's cell phone right now, for example. Certainly the inertial sensors, the gravimeters, the accelerometers, those are very well-established systems, but they're too big and they're too expensive to really deploy widely at this point. That said, there are emerging technologies that are required for almost all of these based on photonics that will bring the price point down over the next 3 to 5 years. And taking clocks as an example, that same technology that we're able to deploy in a large box rack-mounted unit today will probably come from a couple $100,000 down below $10,000 on the 3 to 5 year timeline by bringing in the new photonic capabilities that are coming out of what are known as photonically integrated circuits. Again, everything that we do, not across quantum, but certainly across inflection, there's a little home for atoms and there's a laser system. Bringing the cost of both of those elements down will allow those to be widely deployable on a 3 to 5 year timeline.
Thank you. And I'll note, a few $100,000 is still actually a lot cheaper than hydrogen masers. So you'd already be getting a deal there. And then Mike, I know AFRL is doing a lot of work in MagNav and in developing some of these other sensors. Can you speak to this as well, maybe with a focus on MagNav or the Envy Diamond sensors
Sure.
that you mentioned?
Yeah, so we're very focused on getting fielded applications and accelerating that. I think some people might be aware there's a recent DIU announcement that we're deeply tied in with, where we're actually looking at within the next number of years getting both atom interferometry-based inertial measurement units and magnetic navigation fielded and demonstrated in the field to be able to start transitioning that to our DoD partners. And so, I would say within the next, 3 to 5 years, we're going to start to see full 6 degrees of freedom IMUs that can potentially replace existing classical systems. And this is building on that example that Bonnie mentioned that DIU is currently going to be sending up in space. That's a single degree of freedom. So there's a lot of additional development and advancement that needs to get those additional degrees of freedom for a full inertial measurement unit, as well as developing and maturing the sensors for magnetic navigation. We expect within the next couple of years to have sensors that are hardened for aircraft application and meeting all the specs that we expect, and then some more time to make sure that we can go through all of the additional requirements for navigation and then building out maps that we need over relevant areas. So one of the biggest challenges with MagNav and turning that into an actual application isn't necessarily the sensors or the map or the navigation techniques. That's been demonstrated. We've had many demonstrations on navigation. It's really building out the maps over the areas that we need them, because without having a map, you have nothing to reference to. We in most cases can't use existing maps. We actually are going to have to go out and develop and collect new maps over areas that we're going to want to navigate and have that assured capability.
Okay, great, thank you. And then Rishu, you're describing technologies that are maybe a little bit further out. Can you speak to potential timelines for getting those out in the field, and what are some of the current barriers to deploying those technologies?
Thank you, Bonnie, for the question. So actually, it's a really good continuation from both your slides, talking about chemical and bio sensing, and also following Mac's comment on nitrogen vacancy-based, nanodiamond-based ODRMI system. So at NETL, we actually are working on the technology, how to functionalize those nanodiamonds with nitrogen vacancies to achieve a more variety of sensing besides the magnetic sensing. So we currently use the magnetic sensing as our benchmark to make sure our system works. But as you can see in our current expertise, we develop the fiber optic or passive wireless-based sensor devices. We also functionalize those sensing devices. So to us, we are not only developing quantum sensing, we are also trying to functionalize the sensing devices for example, gas detection, related to gas leaks, safety monitoring, and also, as Bonnie mentioned, strain sensing is the inherent property of the nanodiamonds. But those diamonds are very, very hard, as we know, right? So they're very hard. So, but good thing. So basically, you need a stronger pressure change or strain change to generate signals. But the good thing is it's very sensitive, right? So anyway, so I think regarding the device itself, it has an inherent properties change that can be monitored. But how do we, for the next step, how do we functionalize it and bring more sensing capabilities to the quantum sensing platform is the next step, or as you kind of also mentioned. So regarding the timeline, I also really like your timeline chart of the solid state defect devices. So for magnetic sensing, it is in early prototype that stage. So for the chemical and, for example, gas sensing, using that specific solid state quantum sensing device, I think it's probably first of all we need some R&D stage and then prototyping. So if probably in the next, I think in your slide, once again, I really like that slide. It's more further away compared to the magnetic sensing. So probably 5 year to 10 year, but you know, nowadays technology do develop fairly quick now. So that's another note. Talk about quantum sensing, it is actually quite broad. There are some technologies relatively mature, but some technologies are really, so for example, PNT and magnetic sensing and gravity sensing, they are relatively mature, but some of the areas still have a lot of potential to explore. Yeah, and also another top note I want to share is the interdisciplinary team. So, you know, we need physicists to understand the physics. We also need, like, for example, for the functionalization, we also need material scientists who actually, or even chemists, to understand the application and what is the material that actually generate the signal, be able to detect it by the quantum sensing technologies. So that's another note I would share.
Okay,
Yeah,
thank you. So now I'd like to hopefully loop in our audience a little bit more and ask for all of your perspectives on what can stakeholders like DOT do to help further mature and advance these technologies, either on behalf of the whole community or with engagements with your respective organizations. So maybe I'll ask Max for your perspectives first.
So for the later stage technologies, the technologies that are ready to go, what we really need from the DOT and the other federal agencies is opportunities to do demonstrators in the systems that are of interest to you. So I'll take clocks. Clocks are a really good near-term example. Basically, we're competing with GPS. GPS is a free resource. It's really hard to compete against. The number one challenge is what if it goes away? So the clocks provide a very specific opportunity to provide stable time in the absence of GPS. So that is, it's essentially an infrastructure challenge. Just like the internet or networking capability, timing is a infrastructure resource that's driving our economy. We don't have access to that stable time, what happens? For transportation, it's a key element of navigation and positioning systems. So for the systems and the applications that are of interest to the DOT, how do we inject these technologies and demonstrate that they actually provide value in either the worst case scenario that GPS goes away, or on the other hand, how do they actually provide us to improve the services, the performance of the systems that the DOT provides right now? That's what I would really ask. What's of interest to you, and how do we prove that our technology works?
Okay, thank you. Mike, any perspectives on AFRL and DOT working together?
Yeah, certainly. So I would say, from the Air Force perspective, probably the biggest tie-in is to the FAA, and potential alternative navigation solutions that would be relevant to the FAA. Obviously, the use cases are slightly different, between military applications and commercial, but understanding what are those constraints that exist, and how do we adapt some of the needs that or the systems that we're developing to be relevant, and because one of the things that we're increasingly interested in across the military is dual use applications, to be able to help buy down the cost, to not just have the handful of systems that we need for the Air Force, but distribute it more broadly and allow us to buy down that cost for development, and get it out into the field. Really, trying to understand that crossover and where that hits. One of the things that really is, the guide star for us is, right now we're reaping the benefits of the GPS, how it's enabled our economy and our society to develop in the last 20 years. But we're also suffering the consequence of the success of GPS, and that's a single point of failure.
Especially with pipeline safety. So can you speak a little bit more about how they might work well together?
Yeah. Thank you. So that's a really good question. So actually, even for most of the work that we have been working as a pipeline, and also this technology we are working for pipeline actually can be broadly applicable to like transportation infrastructure, roads, bridge. Yeah, so I think first the interagency collaboration would be really nice. I think there are also some activities that's ongoing between the two agencies. And another comment I also like to follow up on, so demonstration opportunities would also be nice as well. So I think those are two things would be very beneficial for the technology development. Oh, the third thing is that I think DOT kind of already took the action to generate that report that for some use cases, it'll be published soon, right? That's the plan. Yeah, so I think that would be also a very nice step, particularly from the public sector, to give some guidance or examples of how quantum technology can be used. I would be very much looking forward to reading that report and see if any, some cases that can be as examples and maybe some cases can be added. Especially, follow up your last question that some of the really relatively out in the future, that should also be, some interest need to be included in that, so people will keep that in mind.
Okay, thank you so much. I know we're trying to wrap up soon. Okay. Yeah, are there any questions in the room here? Oh, yeah.
Stormy Martin. Stormy leads the space, he and the director. And his question is, do you have a sense of the cost range for commercially available magnet and GravNet packages and the maps to make their output?
So maybe I'll ask Mike to first speak to the maps issue, because that's step one, right? Yeah.
Yeah. So the maps, it's a very complicated challenge. So let's see. I think if I remember right, the cost per linear kilometer was something on the order of $70. So if you're generating a map at 30,000 feet, for example, you need to have the line spacing about half the altitude. So you have to have line spacing of 15,000 feet, and you sort of generate that map in that cost over an area. You can sort of figure out what the cost would be. The benefit for, I think, commercial applications is that generally fixed paths of where you're flying reduce the area that you need to have a map over. So it's a significantly lower cost endeavor to create lanes in the road as opposed to a holistic map across the Pacific Ocean. So, being able to target and know where we expect to have navigation should significantly reduce the cost of mapping. So I think that's a significant benefit there for commercial. An exact number, I would have no idea, but it's not going to be cheap, I'll tell you that. But then in terms of systems, I think, right now, if you're looking at building a system, you're probably looking at $50,000. I think, that I would be shocked if we can't drive that down to, below $5,000 within the next 5 years or so. I think the cost of systems will be able to be reduced, especially as the use cases for these magnetometers are continue to expand, which they will. So I don't think that's going to be a huge driver.
Okay, thank you. And yeah, question in the room?
Question to Max is, we have a lot of infrastructure that uses GPS clocks. Is it possible to coexist the GPS clock with the atomic clock on the same platform?
Yes. So the question is, so every GPS satellite has multiple atomic clocks, conventional microwave atomic clocks on them. I think the question, just to repeat, is for the holdover systems that are on the ground, would a practical holdover system have both the ability to receive GPS time and the emerging optical or even cold atom atomic clocks in the same platform? And I think that's absolutely true. I think that's the way you would do it. So basically what happens is there is a onboard local clock, high precision clock, optical clock, cold atom clock, atomic clock on the ground. That's your holdover clock. It is tied to a GPS receiver. So essentially it's disciplined to the GPS system or the GNS system if you're thinking of other satellite navigation systems. So it's disciplined to those distributed systems. When that signal goes away, the holdover clock detects that that signal is not available, and it starts. And it's at that point your worry starts increasing, because eventually that clock will start drifting away from the absolute known as the universal timing coordinate, or the UTC, because it's not disciplined to GPS anymore. So that local system will have a GPS receiver, and it will have a high performance holdover clock in the same box, so to speak, so that during regular operation, it's being constantly disciplined to GPS. In an event where GPS is not available, the holdover clock takes over and then starts distributing the local time for some period without GPS. Now, in the case of the newly emerging optical clocks, they might go for a week or maybe 10 days and still have timing that is commensurate with the GPS time. For some of the more advanced laboratory clocks, it might even go up to a month. But current technology, say based on chip scale atomic clocks, microwave atomic clocks, maybe you get a few hours to a day of holdover, and that's not really long enough for a major GPS disruption event. So to that, okay.
I think with that, we'll thank our panel and keep moving on. Yeah, okay. Thank you.
Introduce two folks. Do we have, is John here with us? I haven't seen, oh, John, wonderful, there you are. And so John and Alan, they will come up. Alan will start with the quantum key glossary, and then John will facilitate our audience-led questions.
Add some things. So a lot of you heard different terms this morning. Yaakov had mentioned NISC era as well. The goal of this next 20 minutes is get all your questions out. And this is for the virtual group as well as the live audience here. Get all your questions out, because we go into breakout groups pretty shortly after lunch. And the goal is, let's not talk about quantum anymore. And what is quantum? Let's talk about how do I apply quantum. So be ready with your questions.
Great.
Like quantum inspired, for example, right? I think that was a really important point as well, Risha. Like, how do you make hybrid sensors, for example? So what is a hybrid sensor? Yeah, keep your questions ready.
Okay, which one? Anyway, yeah, as Prachi said, the objective of this little piece here was to bring everyone up to the same basic level of understanding before we go into the workshops this afternoon. So the quantum experts in the room, please bear with me, especially when I decide maybe you're better to answer or address something than I am. So Yaakov did a great job. These are great panels this morning. So that makes it a little easier for me, a little not easier in the fact that there was no reason to prepare, because I didn't actually have any idea where the gaps were going to be. So, but I want to start with a few things that I heard or didn't hear this morning before I kind of go into what I wanted to hit. People kind of, in my opinion, underplayed the immense challenges in order to actually make this happen. They're throwing out, oh yeah, 5, 10 years, whatever. Every single challenge, every solution to every challenge makes one of the other problems worse. Okay, I spent 2 years looking at this. We interviewed, I'm at Volpe, by the way. Okay, good, says it. talked to dozens of experts and got a wide variety of opinions. So I was glad to see on your earlier panel, everybody wasn't singing the same tune because we didn't hear the same tune. And I was impressed to see how polite people were with each other in public. And I'm going to just stay polite and I'm going to leave it here. But every single solution to a problem that somebody came up with made one of the other problems worse. Okay, so until that is kind of addressed, you're going to have that massive uncertainty. To the fellow that asked about the assembly coding, okay, I took part of a quantum computing course. And at this point, they are programming 1 qubit at a time. That's how you write a program. So that's like when I was in grad school and I found an old IBM magnetic memory core with wires and little loops there. And I was like, oh my God, people used to program these little cores 1 at a time. Well, that's how you program a quantum computer now. And so just let me finish this part. So the programs people are writing now may end up becoming assembly routines in the future that'll be built on. So it's kind of not a waste of time. But if you're application focused, like I'm a little more application focused, do I really want to, be trying to manipulate the state of 1 qubit at a time, or don't let people like these guys do it so that I can come in and work with like a Fortran program? I'm just dating myself by saying that. Sorry, I probably should have said Python, but it's too late. You wanted to make a comment? Sure. Yeah, no, that's great. I'm going to have to, when I give this presentation to our sponsor, I'm going to have to use that one. And yeah, so those are the other things. A little later, I'm going to mention quantum inspired because I think Jonathan's going to be better to answer that, but I don't want to kind of break up my flow here a little bit. Okay, so let me go to actually a real slide here. All right, this is where this isn't really addressed explicitly, and if you understand digital computers, you're probably even at a disadvantage. But quantum gate, we talk about gates. A regular computer, your quantum gate is an electronic circuit on a chip. It's a thing. You turn it on and off. When they talk about gate in a quantum computer, it's not a thing. It's an operation. It's blasting the little ion with a laser beam or a microwave beam or something like that. In a deterministic and reversible way, you transform the qubit state, okay? So instead of clicking transistors at a 10 gigahertz range or nanosecond rate, you're hitting the little, I'm using ion traps as a moment, but you're hitting it with like a laser beam or something like that for a certain dwell time that you need. So quantum gates are much slower than a gate in a digital computer, like by 10,000 times slower, okay? So the consequence is, their quantum gate, the quantum speed comes from parallelism, right? That's why some problems are not suitable for quantum calculations, and we heard that earlier. Where the parallelism helps you, it overcomes this like 10,000 to 1 slowness in the gate speed, and they'll excel at certain things. But other problems, and as Franz was saying, the conventional computer is always going to beat the pants off of a quantum computer. And I like the fact that he alluded to, but I want to emphasize the fact that people go on about their quantum supremacy. Well, the bar is moving every day because the quantum computer folks aren't sitting there taking it easy. And the new large language models that have showed up have accelerated what classical computers can do and have raised the bar again. So when people talk about, oh yeah, quantum computers would be good for machine learning. Well, guess what? Machine learning is making it harder for you to catch up right now. So that's so people put these things in simple terms, especially when they're trying to raise capital for their, venture capital. And there's a big difference between the VC type of folks at the small companies we talk to versus like people at like DARPA and people actually doing research in the universities. So the other thing is a much higher error rate. And you get variations in control. So like a gate in a digital computer, you flip the thing on and off and you get your 0 voltage or your 1 voltage. But when you're shining a laser at a little atom, that's like not necessarily easy to do, to move from one atom to the other, right? So you get variations in your control signals. So the error rate Fellow this morning told me that Microsoft just announced an improvement in error rate by a factor of, the slide said 800 times. That sounds impressive, but, oh, okay. Quantum computers have an error rate 10 to the 15th time worse than a digital computer, a quadrillion times worse, 10 to the 15th. So if they improved it by a factor of 1,000, they've only got trillions to go. So it's not as easy as people kind of make it sound, which brings me to the next thing, which is a term that was explained a little earlier, was the NISQ computers, noisy intermediate quantum scale. So the universal gate computer has got to solve that error problem. You're going to need massive error correction mitigation to get around that. And that requires tens to maybe 1,000 physical qubits to form one logical qubit. So when people say, oh, I've got a 1,000 qubit computer right now, you got to ask them, are you mean physical qubits or logical? And if they're just talking physical qubits, they may only have 5 logical, that may be like a 5-bit computer then. So that's another thing that, you know, if you're new to this kind of stuff, it might be a little confusing. So what the NISQ folks are doing is, okay, we'll take the quantum computer the way it is now with the errors. How is it still useful? For people like us, this is interesting because it's near term. Solving that error problem is going to take, well, I don't want to give timelines either, but you notice the experts weren't giving you real, they were all fuzzy on it for a reason. So potential uses are like quantum emulation, emulating a system, right? So you got your qubits, instead of trying to make a precise mathematical calculation with them, you just use it as a system of qubits to model a system of other particles or components, like a molecule or a galaxy or planetary system, and you stimulate it and you kind of see what happens. And then quantum sensing kind of is the other one. The problem with NISQ, though, is you can only run shallow algorithms, which means there's a limited number of operations you can perform before you lose coherence. So that kind of constrains what you can do with NISQ, but is kind of the near term. Hybrid quantum computer already came up. People doing some of their problem with the classical, going to quantum, then classical back. In my opinion, every quantum computer is a hybrid, because the only way you can control the lasers and all that is using a digital electronic computer in the front end anyway. So the other extreme is, as there was Franz mentioned, it will just be a little niche processor, you know, quantum processing unit, just like the GPU is in your laptops now. And let's see. Oh, and the other thing is, another biggie is, what do people mean when they say quantum computer? Nobody really actually said that. Well, a theoretical physicist named David DiVincenzo proposed some criteria as how we can everybody agree on what's a quantum computer. And basically, oh, and I'm not even moving my slides here. So this is the one on hybrid. This is the one, and oh, by the way, my handout, would somebody? I've done a lot of risk mitigation, and I've actually showed up where the PowerPoint didn't work, so I'm covered. And this way you can take it home with you. If there's information here that's helpful, maybe we don't need to answer any questions. But okay, a quantum computer is, you need to understand your qubits' behavior, and you need to scale to a lot of them, right? You need to be able to reset them to the same starting point, and they need to last long enough to do a useful algorithm, right? You need a standard way to code them. And let's see, yeah, I got that right slide up. And you need to be able to measure the qubits individually. And then lastly, to be able to convert between a stationary and a flying qubit. So like a photon, you may use to move the information to another part of the computer and back, and then do that without decohering. All right, so the rest of this, I'm fortunately out of time, and I don't have to go on about. But in the presentation, you'll see slides that I prepared for our sponsor at the ITS Joint Program Office. So maybe that'll answer some questions that'll bring everybody up to the same level. Or if you look at that right now and have questions, you can ask them now. And let me just start by letting Jonathan explain quantum inspired, since that's interesting to him.
So within QEDC, I'm the deputy director. We are an association and a public-private partnership that was founded in response to the National Quantum Initiative Act in 2018. We're now in our 5th year, and we're an industry-led group. We have 250 member organizations we work with, plus an additional 45 agencies we engage with staff at. So all of the DOT people in the audience today are welcome to fully participate in QEDC and our activities. We have a number of resources we make available, in particular to our government partners, and these include reports like our report on transportation and logistics applications for quantum computing, like our report on the applications of quantum sensors. And we also have a very active set of work groups that meet every week to every month on a variety of topics from workforce and regulation and policy through the specific applications of technology. And they even develop, they carry on ongoing projects, including a set of application-inspired performance benchmarks. So if in the course of the discussions today, there are particular types of problems that you're looking to solve in your work, you're welcome to download our open source software, look at the 4 now manuscripts we published on its application, and begin to see how these quantum algorithms can fit into your workflow and see how they perform on simulators today and on actual quantum hardware today and into the future. So I just wanted to take a moment to put that plug in there. And turning back to you, Alan, you've published this guide, this quantum glossary, as a resource for the department. What drew your interest to this, and why was now the right time?
Actually, I'm not the right person to answer that. You'd have to answer the sponsor, is why did they ask us to look into it? I know the reason they did is they were trying to figure out what to do with their portfolio of research. And because AI was looking like it was pretty slow, they thought, oh, maybe we ought to move some money into quantum. Now, in the middle of doing this, guess what showed up? Large language models. And so, we'll kind of see. But one other thing in doing the research that I learned from some of the experts we talked to is that, all right, so the hardware might not show up while I'm alive even. The far out estimates on the line was like 2070, and I know I'm not going to make it that far. But developing the algorithms also can take a really long time, because you can't necessarily port an algorithm to, even though the quantum computer will be universal gate, you have to structure the algorithm differently. Because like I said, the gates are operations, right? So code for a quantum computer looks like sheet music. It doesn't look like lines of Fortran code. And I'm kicking myself that I didn't bring a picture of a quantum program or even a couple of quantum steps so you can understand that. So the need to rethink and restructure the problems the way you solve them on a regular computer so that it fits the quantum computer may take almost as much time as to develop the hardware. So from that point of view, it is probably worth it for the department to start developing some internal expertise in thinking through quantum algorithms, because you got to do that before you get to the coding. And by the time we get to coding, hopefully it's not going to be like assembly language. And the transpiler problem will have been fixed, as Franz said, in the next 10 years. And I was thinking, gee, 10 years, huh? But that is part of the problem, is you write the code on your digital computer, then you have to transform it into quantum code that's machine specific. So the Qiskit thing Thomas mentioned is an attempt for people to try to standardize it so you can write your program with standard functions, but this transpiler will translate it for whatever kind of computer you're trying to work with online. So from that point of view, we probably should be thinking of the applications, and then how do you restructure this to make sense for a quantum computer? As Franz was saying, people are doing that for the classical computers and making them even better, moving the bar. How's that?
That's good. And we are looking to engage the audience and answer your questions before we go to lunch here to help whet the appetite. I have one more question for you, Alan. And that's thinking about my professional life, my laptop and my cell phone are incredible productivity tools. I could not tell you how much RAM is in them or what the clock speed is on the processor. So we now all have this guide, all of these terms relevant to quantum systems. Which of the definitions do you find are most salient to the end user as they consider the application of quantum technologies? And which of the concepts would you consider more under the hood?
He didn't tell me he was going to ask me questions. I thought we were going to come up here. Good move. So I get to be in the hot seat here because I was going to buck all the audience questions to him. So I guess he knew that. The stuff that's under the hood, like what I was talking about, understanding the difference in how they work, how the gates are different, helps you understand why quantum computers can't go certain places and why they're really good elsewhere. So when you're trying to figure out, well, what application can it work on, you need to understand enough about the quantum so that you're not saying, oh, I'll just make what my laptop does better. So choosing the proper use case, knowing enough. So that's why I hit on the gate thing and kind of the hybrid thing and stuff like that. The stuff that's under the hood, I don't know, don't even need to tell them. They don't need to know, right? Like I said, if you're lucky, you won't, somebody internally needs to know how to write your code your quantum program for you, but maybe you can let somebody else do that. And it'll be maybe it'll be a long time because you've got to figure the algorithm out. So I'm not sure if it's the hardware stuff, but it's the software and the algorithmic part that really needs our thinking before, and because the hardware is going to change before we get that figured out, I think. I saw a hand there first.
How to write this way, the machine will do it much more efficiently. How can we get the same how to write a think algorithm?
You're asking me? I think so. I think that's. I think there's. I'm gonna throw the hot potato to them. I think it's gonna be a while. Go ahead. Sure.
I mean, I would defer to the gentleman from IBM. Qiskit is actually a really good. There are languages out there. So I'm Courtney Rolson from Continuum, and I was actually going to make a few comments on just, full disclosure, I used to work at a national lab. So worked in the DOE system and joined the quantum world almost 4 years ago. And I think there's this problem I see all the time in quantum where people want absolutes from us. They want absolutes. They want, when are we going to have this? When are we going to do this? The fact of the matter is, we're pushing the bounds of science every single day. And we're doing things that have never been done before. Just like they did when they developed the original computing systems. And I would say from a Department of Transportation perspective, and one thing, and I've worked a lot with Rob from National Renewable Energy Lab, what is extremely useful and what I see happening a lot in the field, especially in the academic world, are getting subject matter experts like DOT, understanding your problem sets, and getting them with quantum people to help figure out how to start mapping those problems over to a quantum computer. It's not impossible. It is done. But I think that there's this gap right now between those two things, right? There is a lot of work in quantum algorithms. There's a ton of work. We have a team looking at tensor networks in quantum algorithms. There are strides, huge strides being made in that area on the algorithm side, on the hardware side. But when I look at it from a DOT perspective and a use case, it's really handy to sit down with people who are trying to solve problems in their area and say, what is your problem set? And get with a quantum, get with the teams and say, I think the woman from D-Wave said this. How are we going to solve this piece of the problem? Because I think the quantum industry, at least from my perspective, having been in it, is under no illusion. We've never said, or maybe some people have, but most people say these are being developed to complement classical computing, not replace. So how do we start solving part of the problems we can't solve now quantumly and still use classical systems together? And that might be a manual effort right now. That is very well the case. But I would also say, from a perspective of the industry and understanding use cases, we need to start working with people now to understand how to, these very tiny problems, what can be done quantumly, push the bounds of the system, helping understand, are there improvements on the algorithmic side, and scale those problems as the systems scale. And we'll start understanding it is still research, but I think these are potentially a very powerful tool. But I think this is the kind of conversation that's really useful. But I also want to point out that people do want absolutes from us. And the fact of the matter is, a year and a half ago, 2 years ago at Quantinuum, we finally solved a massive problem, trapped ion, which is ion transport around junctions. It's a problem that's been worked on for a long time. So we are making progress. It's just, I would challenge people to look back to where we were 4 or 5 years ago.
I'd love to just add on to that. What D-Wave has found, and we're not the only company who's found this, is that as you work with different companies to identify the problem and start to develop an algorithm together, so you can work with MITRE, you can work with the national labs, you can work with companies directly. There are also professional services like Deloitte's and Accenture's that are all building these algorithm-specific training programs. What we have found is the companies that have come for one problem and they work with us and we help them with the algorithm development, all of a sudden they go off and build a solution for the next problem. So that happened, actually, nobody thinks about it as a technology invested industry, but there's a retail grocer that came to us to solve one problem. And now they built a second application, which is in production, that every time a specific e-commerce delivery for their stores is delivered, it's touching a quantum system. So the algorithm development part is hard. It's something that's getting better. I do think as the years go on, there'll be more open source tools and things that are there, but getting kind of rolling up your sleeves and starting to do it, you start to learn, and each system has different, and each company has different ways in which they help with the coding. KISS gets one, D-Wave has their own. I know Quantinuum and others are using different language models as well. It's not kind of universal just yet.
Did we answer your question on the guide?
I would just briefly add that in QEDC, we have a very detailed technical report out on the need for cross-compilation and better portability across algorithms written in a particular high-level language.
By the way, I wanted to mention, Allison mentioned that using the annealer at that port in Los Angeles, it's port 300, Pier 300. The thing is, when I looked into it, the truckers did not see any improvement in wait time there. But the people that brought the annealer in were the crane operators. So they are maybe working more efficiently with less cranes, but it didn't solve the bottleneck. And this is just a general systems engineering problem, is if you make things better where the bottleneck isn't, you make things worse at the bottleneck. So that's another thing. You want to be smart about how you employ this technology to the part of your system where it needs it. Because if you make it better somewhere that doesn't need it, you're going to make the problem worse where it's already congested.
We have Franz for a quick
No, okay, that was only a comment to that. I think the reason was that the digital twin model that they did was actually mainly based on the crane operating and not so much on the truck side. So therefore, this was much better.
Thank you. And we have Ed from Savant X. He will be the moderator in the virtual sessions and can share more about that case study as well. More questions, especially we have Jonathan, we have all our quantum experts here. Any more thoughts, questions from the audience here?
So we develop a new toy called quantum computing. Do we, or is it to be considered, or should we consider the O&M of it once we got it going? However it's implemented, we have to maintain it and upgrade it, manpower, cost, electricity, and so forth.
I think you will.
Actually, just really quickly.
I was going to say you will not. You'll access it online via the cloud because they're cryogenic and finicky. It'll be decades before anybody can like afford to buy one, if ever. I'm sorry, go ahead.
Most of our members do offer cloud services, but there are some members that specialize in on-premises systems where you may have more sensitive workloads. So the products are there to meet the market need.
It's almost a premature comment that the O&M of this technology.
For us, it is.
Yes.
Not for the people, like he said, that want to have their own machine in-house for their own reasons, like the NSA say. I'm just speculating. I don't know anything about NSA visually. So, no, but so I don't think that's going to be a DOT concern for decades.
Oh, but it's taxpayers' money. It's got to be a concern of any federal agency.
You're gonna pay guys like D-Wave or whatever to handle that, and just go online, and it'll be quantum as a service, basically, just like software as a service.
We have one question from the virtual group of how do quantum computers talk to each other? Really quickly, high level.
You take flying qubits.
Over classical networks today.
And then can you then explain quantum networking? And what we don't cover it today. We are really covering computing and sensing, given its application for us. Just high level. There's more quantum stuff.
Yeah, high level, you can entangle quantum states over longer distances, theoretically. There have been a few demonstrations in the pages of Science Magazine and other scientific journals, but I would say of the major applications of quantum technologies, computing and sensing and networking, networking is still the purview of the research laboratories.
Perfect.
I would just say when I mentioned the flying qubits thing, that's part of how people are doing that, is having different kind of qubits for a different function. Ones with a long coherence time you might use for storage, other ones you might use to do your calculation, and then then you may transfer the information to a photon, which is easy to get across to the other side of the rack or the other side of the state, and then convert it back to a trapped ion or something like that. So that's another level of complication, but that's how to do it.
Perfect. Thank you, Alan. Well, thank you, Jonathan. Thank you, Alan. We have lunch outside.